Hello, and welcome to Echoes of the Forgotten Earth, a place where curiosity can settle quietly and science wanders slowly enough to guide you gently toward rest. Tonight's journey takes us into one of the most dramatic cold spells our planet has ever known. Picture the world thawing after a long ice age, glaciers shrinking back, rivers running free again, life cautiously returning to green valleys and wide open plains. Then, almost without warning, the warmth faltered. The chill of the ice age swept back in what felt like an instant and held the planet firmly for more than 1,000 years. Scientists know this interval as the Younger Dryas. You might think of it as the moment when Earth pressed pause on spring and summoned winter back with unexpected force. This is a tale of shifting climates, struggling human communities, and puzzles that scientists are still trying to solve. A world on the brink of transformation, suddenly dragged backward into the cold. Before we begin to untangle what happened, I'd like to know a little something about you. Where are you listening from right now? And what is the weather like beyond your window? Because while we explore a world abruptly frozen, your own surroundings might be warm, or soaked in rain, or already wrapped in your own kind of chill. That small detail, your personal season, links us back to the wider story of Earth's perpetual dance with climate. And if this calm exploration feels comforting to you, or if it helps you drift towards sleep while you learn, a like or a subscription would mean a great deal. It allows this quiet corner to reach others who might also want to unwind with stories of science. There's no urgency, no obligation, just something for you to keep in mind. Now let's settle in, because what unfolded more than 12,000 years ago is more than a chapter of rocks and ice. It is a reminder of how delicate and surprising Earth's climate can be, and how profoundly it shaped the people who had to live through its swings. The Younger Dryas begins at a moment when the enormous ice sheets of the last glacial maximum were already in retreat. For tens of thousands of years, ice had blanketed much of North America, Northern Europe, and Asia. At the peak of that deep freeze, colossal glaciers stretched for miles upon miles, burying mountains, gouging valleys, and grinding down the land beneath. But by roughly 14,000 years ago, that frozen world was changing. Temperatures climbed, ice sheets thinned and pulled back, and vast lakes pooled across the continents. Rivers ballooned with meltwater, ecosystems reorganized, and animals ventured into territories that had long been locked beneath ice. Mammoths, gigantic bison, and other megafauna still wandered these landscapes, but they now shared their shrinking, icy realms with humans who were learning to hunt, to gather, and in time, to experiment with the very earliest forms of cultivation. For a time, everything seemed to be moving toward a steadily warming planet. Forests pushed outward, grasslands brightened, and humans found more chances to linger in one place instead of tracking migrating herds without end. Then something shifted. Instead of continuing into a warmer and more stable climate, the planet slipped abruptly back into cold conditions nearly as harsh as those at the height of the Ice Age. This sudden resurgence of freezing temperatures is what scientists later named the Younger Dryas, after a tough little Arctic plant, Dryas octopetala, whose pollen appears abundantly in ancient layers of sediment and signals a return of the cold. Wherever that hardy flower spread, the chill had come back. What makes the Younger Dryas so compelling is the speed with which it arrived. Within only a few decades, global temperatures fell sharply, glaciers stopped retreating, and in many areas, they began to push forward again. Imagine living in a world where, in the span of your grandparents' lives, a steadily warming Earth suddenly reversed course. Seasons would seem to stretch into prolonged winters. Fields would fail more often, herds would thin, and entire communities would be forced to reconsider how they could endure. And yet, people did endure. They adapted, they shifted, and they survived. Without their resilience, without the persistence of those ancient societies, human history might have unfolded along a very different path. Why did all this occur? That question has driven decades of scientific investigation. Some of the clearest clues lie frozen in deep ice cores drilled from Greenland, where layer upon layer of fallen snow compressed into ice and recorded year-by-year changes in climate. These icy archives show an unmistakable signature of the Younger Dryas, a steep plunge in temperature, roughly 1,000 years of sustained cold, followed by an equally abrupt leap back into warmth. Other clues come from lake sediments, ancient fossils, and layers of charcoal that hint at extensive fires. Taken together, these strands of evidence say that something extraordinary happened, yet the true cause is still argued over. Some scientists propose that changes in ocean circulation, triggered by sudden floods of glacial meltwater, disrupted the usual flow of heat around the globe. Others point to volcanic eruptions that may have clouded the atmosphere, while still others suggest a comet or asteroid impact as the spark. Whatever the ultimate mechanism, the outcome was unmistakable. Earth's climate snapped back into Ice Age-like conditions in a strikingly short span of time. For the humans living through it, this shift was not charted on graphs or written up in journals. It arrived as biting winds, shorter growing seasons, and more difficult hunts. In the Near East, communities known as the Natufians had just started to experiment with primitive agriculture, harvesting wild grains, storing food, and settling into villages. The Younger Dryas forced them to alter their approach, perhaps even pushing them toward more deliberate, organized forms of farming as wild resources declined. Elsewhere, hunting and gathering groups had to trail shifting herds into unfamiliar lands or migrate into regions that felt the cold less severely. These decisions echoed across millennia, influencing where later civilizations would rise and how they would take root. As the cold persisted, ecosystems continued to tilt and rearrange. Large mammals that had flourished in the preceding warming period began to disappear. Some of this wave of extinction may have been driven by human hunting, but the renewed climatic stress of the Younger Dryas surely added to the burden. Without consistent climates and dependable food webs, animals such as the mammoth and the saber-toothed cat struggled to survive. At the same time, smaller, more adaptable creatures took advantage of the opening, filling ecological niches left vacant by the great beasts. When the Younger Dryas finally ended around 11,500 years ago, the planet warmed again with striking speed. In the span of decades, temperatures rose, ice receded once more, and the Holocene epoch began, the relatively stable, warm interval that still cradles us today. For humans, that warming was an open door into a different kind of existence. It paved the way for more intensive agriculture, permanent settlements, and eventually, the complex civilizations whose legacies shape our modern world. In that sense, the Younger Dryas, harsh, unforgiving, and disruptive, may have nudged humanity onto the path that led to contemporary societies. But for now, we are moving ahead too quickly. Tonight, as we step slowly into this story, we will take our time. We will look at the world before the Younger Dryas, at the sudden resurgence of ice, at the competing theories that tried to explain it, and at the many ways it transformed the lives of those who endured it. It is a story of swinging climates, delicate balances, and survival in the face of shifting odds. And it begins with a warming earth, receding ice, and life cautiously reclaiming the land, only to have winter seize it all back once more. Before the great cold snap we call the Younger Dryas, Earth was already undergoing one of the most dramatic transformations in its long history. For tens of thousands of years, glaciers had sprawled across whole continents, sculpting valleys, damming rivers, and shaping landscapes we still recognize in altered form today. At the height of the last ice age, about 20,000 years ago, immense ice sheets blanketed much of North America, Northern Europe, and Asia. In places, they rose miles thick, heavy enough to push the crust of the planet downward beneath them. Entire mountain chains lay buried under frozen walls, and global sea levels stood more than 100 meters lower than they do now, exposing broad coastal plains where people and animals could roam. By about 14,000 years ago, that frozen arrangement was loosening. Subtle changes in Earth's orbit, gradual shifts in its tilt, and climbing greenhouse gas levels were together warming the climate. The massive ice sheets began to retreat. Valleys once clogged with ice brimmed with meltwater, forming lakes so vast they seemed like inland seas. Rivers swelled and surged, reworking landscapes with their periodic floods. Forests began expanding into territories that had long been tundra. Grasses spread across areas that had been barren and windswept. For the first time in many millennia, nature felt as though it were awakening from a long, frozen slumber. For the people alive in that age, this warming was both a gift and a test. Humans had already shown themselves to be remarkable survivors. They had endured the height of the Ice Age by hunting the great mammals of the steppe and tundra, by gathering resilient plants, and by constantly adjusting to harsh, shifting conditions. They moved in small bands, following the rhythm of the seasons, tracking herds of mammoths, bison, and reindeer. Now, as the planet warmed, they encountered new environments. Rivers opened corridors into the interiors of continents. Expanding forests offered unfamiliar game and plants. Along coastlines, where low sea levels had once revealed wide stretches of land, people could walk across areas that would later lie buried beneath the ocean. In this era of thaw, sweeping changes in human culture began to unfold. In the Near East, groups now known as the Natufians started to experiment with a new pattern of life. Rather than roaming constantly, they began building more permanent dwellings. They harvested wild grains, stored seeds, and remained in one place for longer stretches. It wasn't farming in the full sense we recognize today, but it was the first sign of a shift that would eventually blossom into agriculture. Across Europe, people carved figurines, painted cave walls, and left behind art that reflected their beliefs in daily lives. In Asia, communities traveled along rivers and coastlines, trading stone, shells, and ideas. This was a world in motion, warming, greening, and growing more varied. Yet even as the ice retreated, its departure was anything but gentle. The melting glaciers poured out torrents of water that reshaped entire continents. In North America, the retreat of the Laurentide ice sheet created enormous proglacial lakes. One of the largest, known as Lake Agassiz, stretched across hundreds of thousands of square kilometers. It was so immense that it dwarfed today's Great Lakes many times over. These giant basins of meltwater were precarious, held back only by ridges of ice and loose sediment. When those barriers failed, floods roared across the land with unimaginable power. Whole river valleys were stripped of soil. New channels were carved abruptly across the landscape. Some of these catastrophic outbursts may have delivered enough fresh water to the oceans to unsettle the delicate circulation patterns that help regulate Earth's climate. This warming world remained home to an astonishing cast of animals. Shaggy-coated mammoths, tusked mastodons, giant ground sloths, saber-toothed cats, and enormous bison still crossed the continents. Towering birds stalked the open grasslands. These great beasts had thrived in the wide, icy margins of the Ice Age, grazing on tough plants and migrating over vast distances. But as forests crept across the land and climates shifted, their habitats shrank. Some species adjusted, others could not. Humans hunted them, wore their hides for warmth, fashioned bones into tools, and relied on their meat. Living alongside such animals demanded deep knowledge of the land, careful cooperation, and finely honed skills. And in turn, human pressures added to the strain on the very creatures that had sustained them. In Europe, the retreating ice revealed lands that had not seen light or life for tens of thousands of years. The newly exposed soil was raw and bare, quickly colonized by hardy pioneer plants. Soon, stands of birch and pine took hold. Rivers once blocked by walls of ice now flowed unhindered, carrying fish and attracting wildlife. People followed these changes, pushing into these fresh frontiers, leaving behind stone implements and hearths to mark their presence. Archaeological evidence shows that humans often lived close to the ever-receding edge of the ice, advancing as the glaciers withdrew, staying near that shifting line between frozen and free. In Asia, endless steppes stretched across Siberia, feeding vast herds of reindeer and horses. People there developed ingenious strategies for thriving in such severe environments, building shelters from bones and hides, and learning to make full use of every part of the animals they killed. Along the coasts of what are now China and Japan, humans fished, gathered shellfish, and began experimenting with early pottery, one of the first known uses of fired clay in the world. Farther south in Africa, the warmer climate supported expanding savannas and forests, where humans hunted antelope, collected fruits, and lived in diverse habitats that had shaped our species from its earliest days. The world before the Younger Dryas was anything but uniform. The overarching trend was toward warmth, but local climates differed. Some regions remained dominated by ice, while others had already blossomed into forests and grasslands. Everywhere, people were adjusting, discovering new ways to live, trying out tools, and slowly reshaping their surroundings. They set fires to clear land. They cut wild grasses with stone sickles. Settlements became more frequent and more enduring. The first seeds of agriculture and permanent communities were quietly being planted, though no one then could have imagined how far those seeds would eventually grow. It is in this moment of transition of thaw, of promise, that the story of the Younger Dryas begins to loom large. Just as people were settling into new rhythms, just as forests and animals seemed to be adapting and expanding, a sudden return of cold would throw all of it into doubt. Seen from today, it is tempting to treat that warming interval as merely a prelude, a fragile pause before winter's surprise comeback. But for those who lived through it, it must have felt like an age of possibility. The long ice age appeared finally to be loosening its hold. The land was greener, the rivers full of life, and the sky perhaps seemed a little wider. And then, within only a few generations, everything shifted once more. The retreat of the great ice sheets was one of the most dramatic natural transformations the planet has ever seen, and it laid the groundwork for everything that followed. For tens of thousands of years, glaciers had covered vast swaths of the northern continents. In some regions, they piled more than 2 miles thick, pressing the crust down beneath their massive weight. Whole landscapes sagged under the burden of ice. The Laurentide ice sheet in North America stretched from what is now the Arctic Ocean far to the south, beyond the present Great Lakes, covering almost all of Canada and much of the northern United States. In Europe, the Fennoscandian ice complex spread across Scandinavia, the British Isles, and northern Germany, while in Asia, vast tongues of ice advanced over Siberia. Altogether, these ice sheets locked away so much water that sea levels worldwide fell by more than 100 meters. As Earth's orbit shifted and greenhouse gases accumulated, the balance slowly tipped. Around 19,000 years ago, the ice sheets began to melt in earnest. At first, the retreat was gradual, but once it started, it accelerated. Each summer brought longer periods of melting, and each year, the glaciers lost more ice than they gained in winter. The margins of the ice sheets pulled back, revealing ground that had been hidden from the sun for tens of millennia. Life began creeping into these uncovered areas, first mosses and lichens, then grasses, then bushes, and finally full forests where ice had once scraped bedrock bare. Whole ecosystems took root on freshly revealed land. The retreat was not smooth or steady. Sometimes glaciers paused for centuries. At other times, they collapsed in dramatic surges. As they shrank, they released tremendous volumes of meltwater, forming enormous lakes across the continents. In North America, Lake Agassiz grew into the largest of them all. At its peak, it covered an area greater than that of all the modern Great Lakes combined. Imagine an inland sea of frigid meltwater, hemmed in by ridges of ice and moraines of rubble. Similar lakes formed in Europe and Asia, trapped behind the retreating walls of ice. These lakes were inherently unstable. Their ice and sediment dams were fragile. When they failed, they unleashed cataclysmic outburst floods that roared across the land. One of the most famous examples occurred in the Pacific Northwest of North America, events now known as the Missoula floods. Time and again, as an ice dam gave way near what is now Montana, a tremendous body of water burst westward. A torrent equivalent to many of today's largest rivers combined rushed across present-day Washington and Oregon at astonishing speeds. Entire valleys were stripped to bedrock. Huge boulders were carried miles from their source. Deep, scarred landscapes called scablands were carved into the basalt. When these floods reached the Pacific, they altered coastlines in moments. These were not minor disturbances. They were forces that rearranged whole regions in a matter of days. As the glaciers melted and the water returned to the oceans, sea levels rose dramatically. Coastlines shifted inland. Land bridges that had linked continents slipped beneath the waves. The most famous of these was the Bering Land Bridge, which had long connected Siberia to Alaska. It had provided a pathway for humans and animals moving between Asia and the Americas. As the seas climbed, that land corridor narrowed and finally disappeared entirely. Coastal plains that had once stretched far offshore were drowned, leaving only the narrower shorelines we see today. What had been broad hunting grounds, migration routes, and temporary settlements became seafloors, bearing traces of early human presence beneath the rising oceans. At the same time, the land once pressed down under the ice began to uplift. This process, known as isostatic rebound, is the crust's slow response to the removal of the ice's enormous weight. When 2 miles of ice vanish, the rock beneath starts to spring back, but only gradually. Even now, thousands of years later, parts of Canada and Scandinavia are still rising by a few millimeters each year, still adjusting to the loss of their icy burden. For people living on this returning land, the change would have been slow yet noticeable across generations. Shorelines crept outward as the ground rose, rivers changed course, lakes drained or formed anew. The earth itself was flexing and reshaping, recovering from the strain of the ice age. The retreat of the giant ice sheets also transformed the communities of animals that had lived around them. Mammoths, mastodons, woolly rhinoceroses, and giant ground sloths belonged to a suite of large animals often called megafauna, which had roamed during the height of the ice age. They thrived in the open grasslands and tundras that bordered the glaciers, feeding on resilient plants and traveling over vast areas. But as forests spread into those zones and the climate warmed, the environments that supported them shrank. Some species managed to adapt to the changing conditions, but many did not. The warming that followed the last glacial maximum coincided with a wave of extinctions, especially in North America, where many of the largest animals vanished within a few thousand years. Human hunting probably contributed to their disappearance, adding pressure to populations already stressed by shrinking and shifting habitats. For humans, however, the retreat of the glaciers opened new doors. In North America, as the Laurentide ice sheet pulled back, corridors appeared between separate ice masses, allowing people to move southward into regions that had been locked away. Archaeological finds indicate that humans quickly occupied these newly accessible lands, leaving stone tools, hearths, and other traces of their presence. In Europe, as the ice withdrew from Scandinavia, new territories emerged in the north. Hunters followed reindeer herds into freshly uncovered valleys. Rivers turned into natural highways, supporting travel and exchange over long distances. In Asia, changing shorelines and milder conditions along the coast created new opportunities for fishing and gathering in areas that had formerly been sealed in by ice. The retreating ice didn't only change where people and animals could live, it also altered the climate directly. Glaciers and ice sheets act as immense mirrors, reflecting sunlight back into space. When they cover large areas, they help keep the planet cool. As they shrink, darker land and ocean surfaces absorb more solar energy, amplifying the warming that caused the melting in the first place. Yet, at the same time, the torrents of meltwater pouring into the oceans affected the global system of currents that transports heat around the world. These large-scale disruptions to the so-called ocean conveyor may have been among the triggers for the sudden cold reversal marked by the Younger Dryas. Earth was not simply warming in a smooth, steady way. It was heaving and adjusting, sometimes responding violently to the changes being forced upon it. Life in this period sat on a tightrope between opportunity and risk. Newly revealed lands promised more game, more plants, and more sites for human camps or villages. But the same forces that opened new territories also brought unpredictability. A single outburst flood could erase valleys in days. Rising seas could cut off once accessible coasts. Shifts in local climate could move hunting grounds or water sources within a human lifetime. To survive, human groups needed to remain highly mobile and flexible, constantly reading the land and sky. They passed hard-earned wisdom from elders to children, stories of sudden floods, of bitter winds that returned, of land that rose or sank. Such tales may lie behind some of the ancient myths of great floods or frozen ages that still echo in traditional stories today. In the Middle East, the gradual retreat of the glaciers contributed to a climate stable enough for early people to try something new with plants. Wild cereals such as wheat and barley grew in dense stands. Communities began to harvest and store these grains, and eventually they took the first steps toward deliberately planting and tending them. Without the ice's retreat and the new stability it brought, the fertile river valleys and hillsides that would become birthplaces of agriculture and civilization might never have formed as they did. In South America, the melting of mountain glaciers would, thousands of years later, open highland valleys that farming cultures would transform into terraced fields. In that sense, the disappearance of ancient ice was not merely an ending, it was the beginning of entirely new ways of life. Yet the retreat of the glaciers was never a simple, one-directional process. At times, ice fronts surged forward again, reclaiming some of the lands they had relinquished, before withdrawing once more. Climate swings were frequent, with warmer intervals interrupted by cooler spells. People living in these shifting conditions had no way to know what the next century would bring. They could only adjust as quickly and as wisely as they could, relying on mobility, shared knowledge, and ingenuity. What must have looked like the final end of the Ice Age turned out not to be the true conclusion. Earth still had one major surprise in reserve, one last powerful burst of cold that would test everything humans and ecosystems had learned during the long withdrawal of the ice. As the warming gained momentum, rivers swelled and seas crept upward, forests spread, and great animals faded from the scene. The stage was quietly being set for that sudden reversal. The Younger Dryas was drawing near, and the remnants of the retreating ice would once more shape the destiny of the planet. By the time the ice sheets had withdrawn far enough to reveal broad new landscapes, the climate of the Earth had entered a delicate state. The world was no longer locked in the extreme cold of the full Ice Age, yet it had not yet reached the stable warmth that would define the Holocene. Instead, it lingered in a transitional zone, a world on the brink, where seemingly small shifts in temperature, rainfall, or ocean currents could cascade into sweeping changes across continents. To live in that era was to accept uncertainty. Seasons could behave erratically. Rains might fail for years. Cold winds might return just when people had grown used to gentler conditions, and entire regions could swing from abundance to scarcity in only a few decades. For modern scientists, this period stands out as one of the most sensitive and volatile chapters in Earth's climate story. Ice cores from Greenland display wild jumps in temperature, some occurring within only a handful of years. Pollen preserved in lake sediments reveals forests retreating and advancing as though the land itself were breathing in and out. Geological records mark the paths of sudden floods, the shifting outlines of coasts, and layers of dust that signal winds sweeping across dried-out regions. Everything we see in these records suggests that the climate system was unstable, quick to respond to small pushes, and poised between ice and warmth like a balance waiting to tip. One major reason for this instability was the vast volume of fresh water pouring into the oceans. The retreating glaciers were not melting serenely like cubes in a glass. They were disintegrating in torrents, sometimes gradually, sometimes in explosive bursts. These flows emptied into the North Atlantic, the Arctic, and the North Pacific, altering the saltiness of surface waters. Salinity is one of the hidden drivers of global circulation. The ocean's great conveyor belt, often called the thermohaline circulation, depends on contrast in both temperature and salt content to move water around the globe. Warm, salty water travels northward near the surface, cools, becomes denser, and sinks, powering deep currents that carry heat and nutrients around the planet. If too much fresh water is added to the northern oceans, the surface water becomes less salty and thus less dense. It doesn't sink as readily. Slow the sinking, and you weaken the entire conveyor, disrupt it enough, and you can dramatically alter where and how heat is distributed around the globe. Evidence suggests that during this transitional period, such disruptions may have happened more than once. Some researchers argue that sudden pulses of meltwater slowed the Atlantic circulation, cooling Europe and parts of North America even as the southern hemisphere warmed or shifted in other ways. Others point to feedbacks between vegetation, sea ice, and the atmosphere that may have amplified these swings. Regardless of the exact pathways, the outcome is clear. The climate could change at a speed that outpaced both ecosystems and human societies. For the people of that age, these changes were not measured in data but felt directly in the land and sky. Hunters in Europe might have noticed that reindeer herds no longer passed through familiar valleys. Gatherers in the Near East might have watched wild grains fail to ripen during cooler summers. Fishers along the coasts would have observed storms growing harsher or fish migrating to unfamiliar waters. Life in a climate on the edge meant constant movement and improvisation, never knowing whether the coming years would bring bounty or hardship. In many ways, this very uncertainty may have encouraged creativity. When the environment refuses to be predictable, survival depends on flexibility. Groups learned to expand the range of foods they used, to move quickly when conditions changed, and to refine tools and strategies that could cope with surprise. Archaeological evidence shows increased use of grinding stones and other gear for processing seeds and plants. In other places, hunting weapons grew lighter and more efficient, with carefully crafted projectile points designed to conserve material and increase success. These shifts in technology reflect a direct response to a world whose rules were in flux. The animal world echoed these tensions. Cold-adapted species like reindeer and muskoxen prospered during cooler episodes. Other creatures, such as mammoths and mastodons, faced shrinking grasslands and changing vegetation, making their survival more precarious. Predator populations waxed and waned as their prey shifted ranges or declined. Ecosystems that had been steady for thousands of years began to scramble and reorder, like a deck of cards shuffled again and again. To anyone watching closely, the transformations within a single lifetime would have been remarkable. Landscapes they had known since childhood could change permanently within a generation. Open grasslands turning to young forests, familiar river crossings lost to floods or droughts, hills once bare now covered in trees. Dust was another sign of the climate's precarious state. Geological layers from this period show repeated blankets of fine silt deposited across wide regions, carried by persistent winds. Such dust records periods when soils lay exposed and vegetation failed to hold them in place. For people and animals, those dry, dusty years would have been harsh ones, with fewer plants, fewer animals, and more frequent migrations. The dust in the air would not have been an abstract signal, but something tasted, inhaled, and seen in hazy skies. A daily reminder that the environment's balance could not be taken for granted. This delicate balance is the context in which the Younger Dryas stands out so dramatically. It shows what can happen when a system already on edge is pushed just a little further. For roughly 1,000 years, the general trend had been toward warming, though uneven and troubled by setbacks. Forests spread, seas rose, human communities adjusted. Then suddenly, the warmth fell apart, and conditions resembling an ice age returned. The very fact that such a dramatic reversal was possible speaks volumes about how unstable the climate already was. It was balanced on a knife's edge, and all it took was one extra push, perhaps from meltwater, perhaps from volcanoes, perhaps from something falling from the sky, to tip it back into the cold. For scientists today, this period is more than a curiosity of deep time. It serves as a warning. Earth's climate has shown itself capable of rapid, step-like changes, far faster than many people imagine. A world that is warming can suddenly cool. A seemingly stable pattern can snap into a new state. The exact triggers may differ from one event to another, but the sensitivity of the system remains. That sensitivity shaped the lives of people 12,000 years ago, and it is something we are still grappling with now. Those who lived in this climate on the edge left behind traces of how they responded. In the Levant, the Natufian culture shows remains of semi-sedentary villages. stone houses, and the harvesting of wild grains. When the Younger Dryas struck, many of these villages were abandoned or changed as people adjusted to farmland that no longer yielded as before. In northern Europe, layers of animal bones at archaeological sites suggest shifts in diet, as certain prey species disappeared or moved away. In North America, changes in stone tool styles may reflect adaptations to new hunting conditions, as large mammals dwindled. Everywhere, the climate's instability shaped human choices, prompting migrations, fueling innovations, and occasionally contributing to the collapse of particular ways of life. The Earth itself carries the scars of this fragile era. Rivers sliced fresh paths into newly exposed terrain. Coastlines migrated as sea levels rose unevenly from place to place. Catastrophic floods left behind oversized boulders and scoured valleys. Sediments in lakes and seas captured sudden shifts in vegetation, water temperature, and chemistry. Without these records, we would be left with only scattered bones and artifacts. With them, we can glimpse the broader pattern. A world in transition, poised between two states, hypersensitive to every nudge. To imagine daily life in such times is to imagine a level of resilience that's difficult to fathom. Every season carried risk. A particularly warm year might yield more plants, more game, more fish. But if that warmth edged into drought, rivers could shrink and crops could fail. A colder year might bring back herds of reindeer and bison, but extended cold could push forests back and make fuel scarce. Communities had to constantly read the land's signals, the behavior of animals, the growth of plants, the thickness of ice, and respond swiftly. Those who failed to adjust would not last long. Yet despite the uncertainty, life went on. People created art and tools, developed new social customs, told stories, and raised children. They imagined futures despite their precarious present. The climate may have been unstable, but human determination was not. That tension between the unpredictability of the Earth and the persistence of human effort is what carried our species through this perilous interval. As the warming slowly resumed, the sense must have grown in some regions that the Ice Age was finally ending for good. Glaciers shrank, forests expanded, seas gradually rose. But beneath that hope, the reality remained that the climate was still on a knife edge, and Earth was about to demonstrate once again just how swiftly that edge could be crossed. Around 12,800 years ago, just as the world seemed ready to leave the Ice Age fully behind, the climate lurched sharply in the opposite direction. Warming had been in progress for more than 1,000 years. Forests had been spreading, marine shorelines had been creeping inland, and in several places across the globe, humans had begun to establish more permanent communities. Then, almost abruptly, that progress halted. Within a few decades, a blink of an eye on geological timescales, global temperatures dropped back to levels last seen during the height of the Ice Age. In Greenland, ice core records indicate cooling of 10 to 15 degrees Celsius in less than a single human lifetime. Winters lengthened, summers grew cooler. The glaciers that had been retreating slowed, and in many areas, again advanced. Researchers later gave a name to this sudden reappearance of near-glacial conditions, the Younger Dryas, after the small, hardy Arctic flower, whose pollen marks the spread of cold-adapted ecosystems. To understand how abrupt this transition was, imagine elders who remembered a world of increasingly lush forests, expanding plant life, and longer growing seasons. They might have told their children about rivers bursting with meltwater, new grazing lands opening for animals, and a planet that felt as if it were finally emerging from the grip of ice. And then, within those children's own adult years, the warmth would have faded. Rivers would stay frozen longer. Plants might fail to blossom. A chill would seep into every season. The change unfolded so quickly that entire generations grew up under one set of climatic expectations, only to watch them vanish before they aged. The Younger Dryas endured for roughly 200 years. In geological terms, that is the briefest of instants of flicker. But for the animals and people who lived through it, it was effectively permanent. It wasn't a short, cold snap or a minor setback. It was a sustained return to glacial-style conditions, long enough to shape cultures, to refashion ecosystems, and to leave visible imprints on Earth's surface. Then, when it ended, it did so as sharply as it had begun, giving way to the relative warmth of the Holocene, the epoch that encompasses all of recorded human history. The cause of this sudden reversal has been debated intensely. The leading explanation focuses on the oceans. As the ice sheets melted, they had fed vast lakes of fresh water on the continents. The largest, Lake Agassiz in North America, was held in place by fragile walls of ice and sediment. At some point, one or more of those barriers failed. A huge pulse of fresh water surged into the North Atlantic. This influx diluted the ocean's surface, decreasing its salinity and hampering the normal process by which warm, salty water flows north, cools, sinks, and drives the thermohaline circulation. With that system disrupted or stalled, heat no longer moved efficiently into the northern hemisphere. Europe and parts of North America plunged back into the cold. Other scientists have suggested alternative or additional triggers. Some point to volcanic eruptions that might have thrown ash and reflective particles high into the atmosphere, blocking sunlight and cooling the planet. Others propose a more dramatic spark, the airburst or impact of a comet or asteroid. Proponents of this idea highlight unusual microscopic particles and chemical signatures in sediments from around this time, including tiny beads of melted rock and spikes in elements such as platinum. They argue that an extraterrestrial event could have ignited widespread fires, disturbed climate systems, and helped trigger the Younger Dryas. The evidence remains controversial, and the debate continues. It may be that the Younger Dryas cannot be reduced to a single cause at all. Instead, several factors, meltwater floods, altered currents, volcanic eruptions, perhaps even an impact, may have worked together to push the climate past a threshold. For the people living through this upheaval, however, the why was far less pressing than the how of survival. Archaeology shows that human groups were forced to adjust rapidly. In the Near East, Natufian communities that had begun exploring semi-sedentary life and relying on wild cereals now faced colder temperatures and more erratic harvests. Some settlements were abandoned, others intensified their efforts to cultivate plants, steps that may have led directly toward more formal agriculture. In Europe, hunters turned their attention to whatever prey remained or shifted their strategies as big game populations declined or altered their ranges. In North America, the Clovis culture famous for its distinct spear points disappears from the record around this time, replaced by different tool traditions. These new technologies suggest new approaches to hunting and gathering in a more demanding climate. The Younger Dryas was not only about temperature, it also altered rainfall. In parts of Africa, lakes shrank dramatically, turning once fertile basins into arid stretches. The Sahara, which had been comparatively greener during earlier warming phases, dried again into desert. Populations that had moved into those semi-arid zones were forced to withdraw toward more reliable water sources like the Nile. In Asia, the Indian monsoon weakened, reducing rainfall for vast regions that depended on those seasonal storms. These shifts in water availability were as devastating as the cold itself, cutting food supplies, forcing migrations, and creating new strains on already stressed communities. Plants and animals responded in their own ways. Cold-adapted species spread southward again. The little Arctic flower that gives the Younger Dryas its name colonized lower latitudes. Tundra vegetation replaced forests in many regions. Reindeer and other animals suited to cold climates expanded their ranges, while species that had moved north during the preceding warming retreated or disappeared locally. Large animals that were already in trouble from earlier climate shifts and human hunting faced intensified challenges. The Younger Dryas may have pushed some of them over the edge. Mammoths, mastodons, and several other giants of the Pleistocene vanished not long after this interval. What stands out most about the Younger Dryas is not only the speed with which it arrived and the severity of its chill, but the speed with which it ended. Around 11,500 years ago, the cold abated. Within a few decades, temperatures climbed sharply. Glaciers resumed their retreat, and the Holocene began. For human societies, this final pivot was a watershed. With the return of warmth, agriculture spread rapidly. Permanent settlements became common. the long, slow development of complex civilizations began in earnest. Without the end of the Younger Dryas, the trajectory of human history would almost certainly have looked very different. In many ways, the Younger Dryas was a 1,000-year interruption that revealed just how unstable Earth's climate can be. It forced human communities into new patterns, drove ecosystems into new configurations, and altered the course of history. Although it took place 12,000 years ago, its implications remain urgent. The climate system, then and now, is not a slow, predictable machine. It can switch states rapidly. It can surprise. When we talk about the Younger Dryas today, we are not just revisiting an ancient episode. We are looking into a mirror that reflects the fragility of our relationship with climate. The people of that time had no influence over the forces that chilled their world. They could only adjust, endure, and wait for the warmth to return. In that sense, the Younger Dryas is not only a story of the past, it is part of the ongoing story of humans and the planet, a story that continues into our own uncertain climate future. And so, after a long warming, after receding glaciers and slowly rising seas, after new opportunities and cautiously held hopes, the world was thrust back into the cold. The Younger Dryas had arrived, and for more than 1,000 years, Earth remained within its grasp. When the Younger Dryas began, the shift was so rapid that it felt less like a gradual transition and more like the Earth itself had thrown a switch. Regions that had been warming for centuries snapped back into glacial conditions. The transformation was so abrupt that scientists studying Greenland's ice can see the change encompassed in only a few narrow bands of frozen snow. For people on the ground, this meant watching a landscape that had been opening up to new life revert to tundra within a couple of generations. To those alive then, it must have seemed as though the promise of warmth had been snatched away and replaced with the unyielding cold of an ice age that refused to end. Greenland's ice holds some of the clearest proof. Cores drilled from deep within the ice sheet contain temperature records stretching back over 100,000 years. Within that frozen archive lies a sharp, unmistakable plunge at the start of the Younger Dryas. The data show that in less than 10 years, average temperatures dropped by as much as 10 to 15 degrees Celsius. For someone living there, summers that had been growing longer and milder would suddenly shorten. Forests that had begun to take root would wither or retreat, giving way again to scrub and tundra. Rivers that had run freely with meltwater would stay frozen for longer portions of the year. It is this kind of near-instant climate flip that defines the Younger Dryas. In northern Europe, where humans had moved into areas recently uncovered by the withdrawing glaciers, the return of the cold hit hard. Groups that had followed herds of reindeer and bison into newly accessible valleys found those valley floors frozen and barren again. Forest expansion halted abruptly, and tundra plants marched back in. Chill winds returned, reshaping where animals migrated and how people could live. To any community that had believed the Ice Age was fading into memory, the sudden reversal must have felt like a broken promise. In the Near East, where Natufian groups had begun building stone dwellings, gathering wild cereals, and living in relatively permanent settlements, the Younger Dryas brought a different but equally severe kind of disruption. These communities had grown around the stability of a warming climate, which had allowed wild barley and wheat to ripen reliably and game to remain plentiful. With the return of colder, more erratic conditions, harvest became uncertain. Grains did not always mature. Game animals shifted their patterns. Villages that had seemed secure suddenly stood on shaky ground. Archaeological evidence indicates that many Natufian sites were abandoned or reorganized. People had to change how they lived and fed themselves, and that stress may have pushed some groups to take bigger steps toward actively cultivating crop sowing seeds, tending plots, and slowly moving from reliance on the wild to dependence on fields. In North America, the Younger Dryas coincided with profound ecological and cultural changes. The great proglacial lakes that had formed as ice sheets melted continued to send fresh water into the oceans, distorting currents and temperatures. At the same time, the Clovis culture, known for its elegant fluted spear points and association with hunting big game, disappears from the record. Some archaeologists see a link between this cultural shift and the declining populations of megafauna, such as mammoths and mastodons. The renewed cold of the Younger Dryas may have stressed these large animals even more, contributing to their final extinction. As big game declined, human groups diversified their diets, turning more to smaller animals, fish, and plant foods, and developed new tools better suited to this changed menu. The Younger Dryas didn't simply bring cold, it rewrote patterns of moisture as well. In Africa, the Great Lakes of the Rift Valley shrank dramatically. Water bodies like Lake Victoria and Lake Tanganyika, which had been large and productive, dropped to much lower levels. The Sahara once again expanded, returning regions that had briefly been greener to dry desert. Human groups that had ventured north during the earlier warming pulled back toward more reliable rivers and oases, especially along the Nile. In Asia, the weakening of the monsoon system reduced rainfall for millions of square kilometers, altering rivers and the societies that depended on their floods. To those living there, such changes would have shown up in empty riverbeds, failing crops, and the long journeys required to find drinkable water. Fire, too, left its mark on the Younger Dryas. In many regions, layers of charcoal in the soil indicate that wildfires became more widespread around the onset of the cold period. Some researchers argue that changes in vegetation forests dying back and grasslands expanding created landscapes that burned more easily. Others suggest that if a comet or other cosmic event played a role, its immediate aftermath may have included extensive fires ignited by extreme heat. Whatever their origin, these blazes reshaped habitats, killing trees, exposing soil to erosion, and contributing to dust and smoke in the atmosphere. For plants, the Younger Dryas meant contraction and retreat. Trees like birch, pine, and hazel that had advanced northward during the earlier warming were driven back. In many places, forest gave way to open tundra dominated by hardy grasses, mosses, and dwarf shrubs. The spread of the Arctic flower, Dryas octopetala, the namesake of the Younger Dryas, serves as a botanical marker of this shift. For herbivores that relied on woody plants, the change meant reduced food. For predators that relied on those herbivores, it meant reduced prey. For humans, it meant the loss of familiar building materials, fuel, and many edible plants. The renewed cold also altered coastlines yet again. Rising seas from earlier melting had already inundated many low-lying areas. In some places, however, the pause in melting during the Younger Dryas temporarily slowed or reshaped that process. Communities that had adapted to a steadily encroaching shoreline now had to deal with shifting patterns of flooding, erosion, and ice cover. In other regions, outburst floods from glacial lakes continued, periodically carving new channels and sending surges of fresh water toward the oceans. The combination of fluctuating sea levels, sudden freezes, and catastrophic floods made the Younger Dryas a time of constant environmental instability. What is perhaps most astonishing is how quickly this icy interlude came to an end. After more than 1,000 years of cold, the climate once again flipped in the other direction. Within a matter of decades, perhaps even faster in some locations, temperatures rose sharply. To people who had known only the harsh conditions of the Younger Dryas, this second transformation would have felt just as startling as the first. Children who had grown up in sparse, cold environments might live long enough to see trees return, rivers flow more freely, and animals repopulate lands that had seemed desolate. The world changed around them in ways that were impossible to ignore. The phrase, "a world turned cold overnight," captures the essence of the Younger Dryas more literally than it might first appear. In climate terms, a difference of only a few degrees can divide ice from liquid water, tundra from forest, feast from famine. For the people of that era, those differences meant the line between life and death. Yet throughout this tumultuous time, humans displayed extraordinary resilience. They altered diets, migrated, invented new tools, experimented with cultivation, and transmitted survival knowledge from one generation to the next. They endured more than a millennium of severe conditions and emerged into the newfound warmth of the Holocene with new skills and new ways of life. Without such adaptability, humanity's story could easily have ended in that long winter. So as the Younger Dryas settled over the world ice reclaiming land, winds turning sharper, resources growing more uncertain, people once again adjusted. They had already survived the brutal peak of the Ice Age, the early warming, the floods and shifting landscapes. Now they confronted another prolonged winter, a winter that would not lift for centuries. The planet had turned cold again, and humanity's task was simply to keep living within those bounds until warmth returned. When the Younger Dryas tightened its hold, it was not only the thermometer that changed, the entire living fabric of the planet shifted. Plants retreated or vanished, animals altered their ranges or disappeared altogether, and people who had begun to settle into promising new patterns of life were thrown back into the old uncertainties of survival under harsher skies. To understand this period, it helps to see how deeply bound together plants, animals, and humans truly were. None could change without affecting the others. The most visible sign of the renewed cold appeared in the vegetation. Before the Younger Dryas, forests had been advancing northward across Europe and parts of North America. Birch, pine, and hazel trees had pushed into terrain that had been treeless tundra. These spreading woodlands transformed entire ecosystems, providing shelter and food for deer, wild boar, countless birds, and innumerable smaller creatures. With the abrupt return of cold, that green advance stopped. In many regions, forest cover collapsed, replaced by bleak stretches of open tundra dominated by hardy grasses, mosses, and low shrubs. The diminutive Arctic flower Dryas octopetala, whose name was given to the period, spread southward again, a quiet but unmistakable signal that the chill had reclaimed the land. This withdrawal of forests had far-reaching consequences. Herbivores that fed on leaves, bark, and woodland plants found their food supplies shrinking. Predators that depended on those herbivores saw their prey decline. For human communities, the loss of trees meant less readily available firewood, fewer materials for building and tool-making, and a diminished variety of edible fruits and nuts. Within a single human lifetime, valleys once shaded by woodlands could turn into windswept tundra, forcing people to move more often, to change what they hunted and gathered, and to rethink how they built their shelters. Animals reacted quickly to the shifting vegetation. Species adapted to cold reindeer, muskoxen, Arctic hares expanded their ranges. These animals became vital to both predators and humans, offering meat, hides, and bone. Meanwhile, creatures tied more closely to forested environments such as red deer and wild boar retreated southward, trailing the shrinking tree line. For the megafauna, the mammoths, mastodons, giant ground sloths, and others, the Younger Dryas was another severe blow. Already under stress from earlier warming and from human hunting, they now faced stingier habitats and harsher conditions. Many of these large animals did not survive the 1,000 years of cold that followed. By the time the warmth returned, they were gone, leaving only their bones and the faint echoes of their presence in human stories. Predators had to adapt as well. Wolves and foxes shifted as their prey shifted, sometimes moving closer to human encampments as people and carnivores hunted the same animals. Big cats, like the saber-toothed forms that had once ruled certain regions, were already declining. Their specialized hunting strategies made them vulnerable when their favored prey vanished or changed behavior. Smaller and more flexible predators fared better, taking advantage of new opportunities. The entire balance of ecosystems was being reshuffled. In this new arrangement, versatility often made the difference between survival and extinction. For humans, the Younger Dryas pressed on every aspect of existence. In Europe, groups that had ventured into lands opened by the retreating ice were forced to alter their strategies. With larger herds less predictable, people began targeting a wider range of game, including smaller, nimble animals. Archaeological finds show a shift toward lighter, more adaptable hunting tools, designed to be effective against various types of prey. Camps were likely moved more frequently as resources became patchier. After centuries in which some communities had experimented with staying in one place longer, many were drawn back toward older, more nomadic patterns, always ready to move when food grew scarce. In the Near East, the Natufians faced particularly intense challenges. Prior to the Younger Dryas, they had begun constructing stone houses, storing seeds, and relying on wild cereal fields that ripened in the warmer climate. Their lives had been edging toward greater stability, supported by reliable patches of wild wheat and barley. When the cold returned, harvests faltered. Fields that once yielded plenty now produced erratically. Some settlements seemed to have been abandoned. Others responded in a different way. Instead of surrendering their new lifestyle, they invested even more energy into controlling and nurturing plants. Rather than only collecting wild stands, they began deliberately tending them. Over time, this pressure may have led directly to the domestication of wheat and barley. In this view, the Younger Dryas did not simply ruin early farming experiments, it forced them into a more deliberate, organized form. Across North America, human cultures also underwent deep changes. The Clovis people, associated with the hunting of large Ice Age animals and known for their distinctive spear points, vanished from the record during the Younger Dryas. Their disappearance coincides with the extinction of many megafaunal species, suggesting that as mammoths and mastodons died out, the Clovis way of life became unsustainable. People shifted to hunting smaller animals, catching fish, and gathering a broader array of plant foods. This change is reflected in new toolkits better suited to smaller game and more varied tasks. The end of the Clovis culture remains a puzzle, but it is clear that climate and ecological stress were central. Water, too, became less predictable. The return of cold did not merely lower temperatures, it altered the distribution of lakes and rivers. In Africa, shrinking lakes and shifting river courses turned once fertile areas into drier zones. Communities clustered around the remaining dependable water sources like the Nile, fundamentally changing settlement patterns. In Asia, weaker monsoons created drier conditions across large territories, pushing people to migrate, adapt their subsistence strategies, or both. These shifts were felt intimately through wells running dry, through longer journeys to fetch water, through fields that failed. Cold, scarcity, and unpredictability left marks on culture, as well as on bodies. Stress can drive invention, and the Younger Dryas was no exception. People refined their shelters against colder winds, improved clothing to preserve warmth, and learned to store limited food more carefully. They crafted new types of tools suited to their altered surroundings. Yet they did not abandon art or ritual. Carvings, paintings, and symbolic objects from this time show that even amid hardship, humans continued to search for meaning, to express ideas, and to maintain social and spiritual life. Survival was never only a practical matter, it was also about holding communities together in the face of uncertainty. The Younger Dryas may also have left its mark on oral traditions. Many cultures today preserve stories of extreme cold, endless winter, or catastrophic change. While it is impossible to draw a straight line from those stories back to specific events, it is tempting to see in them distant memories of an era like this. Tales of lost beasts, unending snows, or worlds overturned by weather could have their roots in experiences passed down across hundreds of generations, retold and reshaped until they became myth. The freeze was so deep and so long that it is not hard to imagine its memory echoing in story and ritual for millennia. One striking aspect of the Younger Dryas is how uneven its impacts were. Not every region suffered the same intensity of cold. Some places became drier rather than dramatically colder. Others experienced both. The global climate's instability meant that local conditions could diverge sharply. For humans, this mosaic of impacts created both risks and opportunities. While some groups faced steep declines, others discovered ways to prosper in the altered climate. The capacity to move, to share ideas and resources, and to innovate became decisive advantages. The Younger Dryas also influenced which plants and animals would eventually be domesticated. In the Near East, species that could survive on relatively poor vegetation, goats and sheep, for example, were especially valuable and became increasingly integrated into human life. Dogs, already used as hunting companions, were even more important in these harder conditions, helping track and corner game. Plants resilient to cold or unpredictable weather were more likely to be favored and carefully tended. These early choices, made under the pressure of the Younger Dryas, helped shape the later development of agriculture and pastoralism in the Holocene. Throughout this period, the connection between people and their environment was on full display. Every shift in plant communities, each change in animal distribution, and every variation in rainfall rippled through human societies. The Younger Dryas made it clear that humans were deeply embedded in nature, not separate from it. To survive, they had to understand these shifts, adjust to them, and where possible begin to influence them, as they did with the first tentative steps toward farming. As the centuries passed, entire generations were born and died knowing only the conditions of the Younger Dryas. For them, the cold and uncertainty were not disruptions. They were simply the way the world worked. Communities created cultures, traditions, and ways of life that made sense under those constraints. No one living then could have known that within a few hundred years, the climate would soften and the world would change again. It was a 1,000-year winter long enough to shape entire ways of being. And even so, within that prolonged freeze, plants found niches, animals adjusted their ranges, and people devised new strategies. When warmth finally returned, it was these survivors, botanical, animal, and human, that would build the next chapter of Earth's story. But during those long, cold centuries, the world belonged above all to resilience. When scientists first pieced together the history of the Younger Dryas from ice, pollen, and sediments, one question loomed above all. Why? How could the Earth, after spending more than 1,000 years warming, suddenly plunge back toward Ice Age conditions, and then, after more than a millennium of cold, flip back into warmth again just as rapidly? The mystery has fascinated researchers for decades because it reveals how sensitive the climate system can be and how sharply it can change direction. The most commonly discussed explanation centers on the oceans. Our planet's climate is not governed solely by the air above us. It is powerfully shaped by the slow, massive circulation of water through the seas. This global circulation, part of what scientists call the thermohaline circulation, is driven by differences in temperature, thermo, and salinity, haline. Warm, salty water from equatorial regions flows northward at the surface of the Atlantic. As it reaches higher latitudes, it cools, becomes denser, and sinks, forming deep currents that return southward. This sinking of dense water acts like a pump, pulling more warm water northward. In doing so, it carries huge amounts of heat, keeping regions like northern Europe far milder than their latitude would otherwise allow. If that system is disrupted, the climatic consequences can be dramatic. As the great ice sheets melted near the end of the last ice age, they filled enormous lakes on the continents. North America in particular hosted some of the largest glacial lakes ever, including Lake Agassiz, which at its height covered more than 400,000 square kilometers. For thousands of years, these lakes were held back by ice dams and ridges of sediment, but those dams were fragile. When they failed, they did so catastrophically, releasing torrents of fresh water that surged into the ocean. If a sufficiently large pulse of fresh water entered the North Atlantic at once, it would dilute the salty surface layer, making it less dense and less able to sink. Slow or stop that sinking, and the pump that drives the thermohaline circulation falters. When the pump falters, warm water is no longer carried northward with the same force. The result is a rapid cooling in the northern hemisphere, especially around the North Atlantic, while other regions of the world may experience different, sometimes opposite changes. This scenario aligns well with many aspects of the Younger Dryas. It helps explain how the cold could arrive so quickly, how it could last about 1,000 years, and how the return to warmth could be equally abrupt once the circulation revived. Greenland ice cores show a sharp temperature drop consistent with a major reduction in heat brought northward by the Atlantic currents. Sediment cores from the ocean, containing the shells of microscopic organisms, show shifts in species that prefer colder or fresher waters. Chemical signatures in those sediments, including oxygen isotopes, record changes in temperature and salinity that match the timing of the Younger Dryas. All of this evidence points to a significant weakening of the Atlantic circulation triggered by fresh water. Still, not all researchers are convinced that this explanation is complete. Some argue that while catastrophic meltwater pulses certainly occurred, the exact timing and magnitude of those pulses do not always line up perfectly with the onset of the Younger Dryas in every dataset. This has led to additional hypotheses, including the possibility that volcanic eruptions played a role. Large eruptions can hurl ash and sulfur gases into the stratosphere, where they form reflective particles that cool the Earth by blocking sunlight. A suitably timed eruption or series of eruptions might have helped tip the climate into a prolonged cold state. However, evidence for a single eruption of the right size and date remains uncertain, so volcanoes are often seen as a contributing factor rather than the lone cause. The most contentious idea is the impact hypothesis, the suggestion that a comet or asteroid might have exploded over or struck Earth around the start of the Younger Dryas. In 2007, a group of scientists proposed that a cosmic object disintegrated in the atmosphere over North America, releasing energy on the scale of many nuclear bombs. They pointed to microscopic spherules of melted rock, peaks in platinum and other elements, and hints of extreme fires in soil layers from that time. According to this idea, the explosion would have ignited forests across vast areas, sent dust and smoke into the atmosphere, and destabilized already melting ice sheets, perhaps by showering them with hot debris and shockwaves. The combination of fire, smoke, and meltwater could then have driven the climate into the Younger Dryas. Supporters of the impact hypothesis argue that the timing is intriguing. The onset of the Younger Dryas coincides not only with climatic shifts, but also with the disappearance of the Clovis culture in North America and the extinction of many large animals. They suggest a single catastrophic event could help explain all three. Some even speculate that ancient myths describing fire from the sky or world-shaking catastrophes might be distant echoes of such an event. Critics, however, raise serious objections. They note that the evidence of unusual particles and chemical anomalies is inconsistent between sites, and that many of the supposed impact markers can form in other ways, such as through volcanic activity, industrial contamination in more recent layers, or even normal geological processes. Crucially, no undisputed crater of the right age and size has been found. While an airburst like the famous 1908 Tunguska event in Siberia would not leave a crater, skeptics argue that an event big enough to trigger the Younger Dryas should still leave more distinctive geological fingerprints. Over the years, various studies have supported and undermined different parts of the impact case, leaving the scientific community divided. Some researchers propose that the real story might involve multiple interacting triggers rather than a single decisive cause. In this view, the climate system was already near a tipping point due to long-term orbital patterns and progressive ice melt. Meltwater pulses weakened the Atlantic circulation. Smaller volcanic eruptions applied additional cooling. Perhaps even a modest extraterrestrial event contributed further disturbances. Together, these forces nudged the system across a threshold, after which internal feedbacks locked in the Younger Dryas condition. The climate, once pushed, may have chosen a cold state and stayed there until boundary conditions changed enough to allow a flip back to warmth. Complicating the picture further is the fact that the Younger Dryas did not affect all parts of the globe in the same way. While northern Europe and Greenland cooled dramatically, some areas in the southern hemisphere warmed and rainfall patterns shifted unevenly across the tropics. Monsoons in Asia weakened, whereas parts of South America saw increased precipitation. Any explanation must account not only for the sudden cooling in the north, but also for this broader reorganization of climate. A disruption to the Atlantic circulation fits this pattern reasonably well, because it would change how heat and moisture are transported across the planet. But other factors likely modulated the response in different regions. For the people living at the time, the underlying causes were invisible. They did not know about salinity, orbital cycles, volcanic aerosols, or cometary fragments. What they knew was that the weather changed, that familiar resources disappeared, and that old ways of living no longer worked as they once had. The Younger Dryas was, for them, a direct experience of hunger, cold, and uncertainty. For us, understanding the causes of the Younger Dryas is more than an academic exercise. It offers a window into how the climate system behaves under stress, and how seemingly small changes like an influx of fresh water or a burst of aerosols can have outsized effects. Today, the Atlantic circulation shows signs of weakening under the influence of modern warming and the fresh water from melting Greenland ice. While a full Younger Dryas-like shutdown is considered unlikely in the near future, even a significant slowdown could reshape regional climates, affecting agriculture, fisheries, and economies. In this way, the Younger Dryas is both a mystery and a guide. The pieces of the puzzle ice cores, lake sediments, fossils, and artifacts are gradually coming together, though the full picture remains incomplete. As we refine our understanding of what happened 12,000 years ago, we also learn more about the system we inhabit now, its strength, its fragility, and its capacity for sudden change. And so, even as scientists continue to debate meltwater floods, volcanic contributions, possible impacts, and climatic tipping points, one message has already emerged. Earth's climate can, and sometimes does, shift quickly. The Younger Dryas was one such moment, a 1,000-year reminder that the climate is not fixed but dynamic, sensitive, and occasionally unpredictable. When people hear about the Younger Dryas today, one explanation surfaces again and again: a disruption of the ocean's great circulation. To grasp why that idea holds such power, we need to picture the global movement of seawater as a sprawling, interconnected conveyor system, slow but immense. It is not a simple loop, but a tangle of currents driven by differences in temperature, salinity, and winds. Warm saline water from the tropics travels northward at the surface of the Atlantic. When it reaches higher latitudes, it cools, and because it is salty and dense, sinks into the deep ocean. This sinking water then flows back southward at depth, eventually rising elsewhere and helping to complete a global circuit. As it moves, this circulation transports a tremendous amount of heat. Without it, northern Europe, for instance, would be far colder, more like parts of Siberia than the relatively mild landscape we know. This system, the thermohaline circulation, is a core engine of Earth's climate. By redistributing heat from equator to pole, it helps moderate regional temperatures. It also plays a crucial role in ocean ecology, bringing nutrient-rich deep waters up to the surface in some places, feeding plankton and sustaining marine food webs. But this engine depends on a delicate balance of salt and temperature. Add too much fresh water to the North Atlantic, and the surface water becomes less salty and thus less dense. When it cannot sink, the circulation slows. If it slows enough, heat is no longer transported northward in the same way, and the climate can change rapidly. This is why scientists studying the Younger Dryas pay such close attention to floods of meltwater. At the end of the last ice age, lakes like Agassiz were vast reservoirs of fresh water perched at the edges of retreating ice. For long periods, they remained relatively contained. But when their icy or earthen barriers broke, their waters poured toward the ocean. The idea is that one or more of these floods delivered so much fresh water to the North Atlantic in a short time that the normal sinking of dense surface water was disrupted. With the sinking weakened, the conveyor slowed, and the northern hemisphere cooled dramatically. Evidence of this disruption comes from multiple lines of inquiry. Sediment cores drilled from the Atlantic seafloor capture changes in the tiny organisms that live there. Some microscopic species prefer warmer, saltier waters. Others favor cooler, fresher ones. In cores that span the Younger Dryas interval, we see abrupt shifts in which species dominate. Chemical measurements of oxygen isotopes in these same shells also show changes that correspond to cooler temperatures and altered salinity. Together, these clues paint a picture of a circulation system that slowed or reorganized at precisely the time the Younger Dryas began. Greenland ice cores provide another perspective. The temperature drop recorded there is exactly what one would expect if northern heat delivery from the ocean were sharply reduced. Meanwhile, regions farther south show different kinds of changes in rainfall and temperature, consistent with a global reshuffling of heat distribution rather than a uniform cooling. The conveyor belt hypothesis does not answer every question, but it explains many key features of the Younger Dryas: its sudden onset, its 1,000-year duration, and its abrupt end. Once the flood of fresh water subsided and salinity levels recovered, the circulation could restart, bringing warm water north again and allowing temperatures to rebound quickly. For the people living at that time, this deep machinery of the ocean was invisible. They experienced its consequences as bitter winds, erratic seasons, and shifting ecosystems. Yet now, with tools and models they could not have imagined, we can see that something as intangible as the density of seawater thousands of kilometers away may have dictated the fate of their climate. What makes this theory even more compelling is its relevance to our present moment. Measurements today suggest that the Atlantic circulation is weakening, likely due in part to the fresh water now entering the North Atlantic from melting Greenland ice and enhanced rainfall. While scientists do not expect a sudden Younger Dryas-style shutdown, they warn that even a noticeable slowdown could affect weather patterns around the Atlantic basin cooling parts of Europe, influencing monsoons in Africa and Asia, and altering storm tracks and sea levels. The ocean conveyor thus serves as a powerful symbol of how interconnected Earth's systems are. Ice sheets on land influence currents in the sea. Those currents influence the climate in the air. Climate, in turn, shapes ecosystems, agriculture, and human societies. The Younger Dryas was not caused by ocean changes alone, but those changes may have been the central mechanism through which other forces like meltwater floods, or perhaps even explosive impacts, translated into global climate upheaval. Scientists still debate the finer points. Did the fresh water come only from Lake Agassiz or also from other meltwater sources? Was its release a single catastrophic event or a series of rapid pulses? Did the circulation stop completely? Or did it simply slow and shift its pattern? These questions matter for reconstructing history in detail. But at a broad level, the lesson is clear. The thermohaline circulation, powerful enough to regulate much of the northern climate, is also fragile enough to be disrupted by surges of fresh water. This fragility is why the Younger Dryas is such a vital case study. It shows that climate change is not always slow and gradual. Sometimes the system crosses thresholds, and then change can unfold remarkably quickly. That is as true for warming as it is for cooling. The same circulation that likely plunged the world into a 1,000-year winter at the end of the last ice age is still operating today beneath the waves, quietly ferrying heat. If it were to weaken too much, the effects would reverberate across our planet. For the societies of 12,000 years ago, the faltering of this unseen current meant the sudden loss of a warming trend they had come to rely upon. For us, its potential weakening offers a warning about the kinds of surprises the climate system still holds. The Younger Dryas gives us a rare, detailed glimpse of what such a disruption looks like, and a chance to consider how we might respond if something similar, though not identical, unfolded in our own time. And so, the Great Conveyor, normally steady and hidden, emerges in the story of the Younger Dryas as a key actor one that may have translated meltwater floods and other disturbances into a global climate event. It was likely not the only factor involved, but it may have been the crucial link through which local changes became a worldwide transformation. If the Younger Dryas was indeed triggered by disruptions to the oceans, then the colossal floods of meltwater from retreating ice sheets were among the most important culprits. These were not ordinary river floods. They were events of such scale that it can be difficult to imagine them from a modern perspective. Near the end of the last ice age, immense lakes collected along the edges of melting ice sheets, their waters dammed by walls of ice or by ridges of debris bulldozed forward by glaciers. These glacial lakes held volumes of water comparable to modern seas, silent reservoirs poised for disaster. When their barriers failed, the result was not a gentle leak but a roaring release, with consequences that extended from continental interiors all the way to the global climate. Lake Agassiz was one of the greatest of these bodies of water. It formed in central North America as melt streams from the Laurentide ice sheet pooled in low-lying basins. At its maximum, Lake Agassiz occupied an area larger than all 5 of today's Great Lakes put together, spreading across what is now Manitoba, Ontario, Minnesota, and North Dakota. It was held in place to the north by the ice sheet and to the south by a combination of topographic highs and glacial debris. For millennia, its level rose as more meltwater poured in. But all the while, its stability was precarious. The ice and sediment that confined it were vulnerable to cracking, melting, and collapse. When Lake Agassiz finally drained, it did so catastrophically, and likely more than once. Some estimates suggest that, in a single outburst, enough water escaped to raise global sea levels by several meters. Rivers downstream swelled to unimaginable sizes. Entire valley systems were abruptly reamed out by the racing water. Boulders bigger than houses were ripped from the ground and hurled far from their origin. The Missoula floods in the Pacific Northwest are another dramatic example of this kind of event. There, repeated failures of an ice dam allowed a glacial lake to fill and burst again and again, each time sending an ocean's worth of water pouring across eastern Washington and Oregon. These flood-sculpted landscapes still visible today channeled scablands, dry coulees, enormous ripple marks preserved in stone. When glacial outburst floods reached the oceans, they introduced pulses of fresh water capable of altering salinity on a basin-wide scale. In the North Atlantic, where the sinking of dense water drives the thermohaline circulation, such freshening would have disrupted the normal patterns of sinking and mixing. The surface layer, made lighter by fresh water, would resist plunging into the depths. With that sinking weakened or halted, the supply of warm water to high latitudes would falter. Heat that once flowed toward the north might be redirected or retained elsewhere, reshaping global climate patterns. The traces of these enormous floods can still be read in the landscape. Ancient shorelines of glacial lakes appear as long, level terraces high above current plains. Deep channels, far larger than any river that flows there today, cut across bedrock. Thick deposits of sediment fill lowlands where floodwaters once slowed and dropped their loads. Isolated outsized boulders, glacial erratics, sit where floodwaters abandoned them. Geologists reconstructing the end of the Ice Age see in these features a history of repeated outbursts, each capable of disturbing not only local topography, but also global climate. The timing of a major outburst from Lake Agassiz or a similar lake aligns closely with the start of the Younger Dryas, around 12,800 years ago. Whether this took the form of one truly colossal event or a rapid sequence of slightly smaller ones, the net effect would have been a large injection of fresh water into the North Atlantic. In climate models, such a pulse is enough to weaken the Atlantic overturning circulation sharply and trigger a cooling similar to what we see in the records. For the people who lived near these lakes and outflow channels, the floods would have been terrifying. Imagine a lake stretching to the horizon suddenly draining, its waters funneling into a valley at astonishing speed. Lowland camps could be drowned within hours. Landscapes that had sustained families for generations might vanish in days. To escape, people would have had to flee to higher ground with little warning, leaving behind tools, food stores, and perhaps the bodies of those who did not move fast enough. The experience would surely have seared itself into memory. It is easy to see how such events could become the seeds of later myths, stories of deluges sent by gods, of lands swallowed by water, of worlds remade by flood. In the longer term, the floods reshaped environments far from their sources. New lakes formed where floodwaters pooled in low-lying basins. Rivers sometimes rerouted, their courses diverted into new paths carved by the torrents. Sediments spread over floodplains, enriching soils in some regions while burying them in others. Coastlines shifted as the ocean absorbed the influx of water and sea levels rose. For people and animals, this meant that familiar places could become unrecognizable in a single generation, while new, potentially fertile areas appeared elsewhere. By disrupting ocean circulation, these glacial floods helped tie local catastrophes to global climate shifts. The Younger Dryas may, in this sense, be understood as one of the planet's most dramatic examples of how changes in one part of the Earth system, melting ice and draining lakes, can ripple through oceans, atmosphere, ecosystems, and ultimately, human societies. The scale of those outbursts is almost beyond comprehension. Picture standing on a broad plain and seeing in the distance a moving wall of water towering tens of meters high, filled with ice chunks, trees, and rocks, roaring forward with unstoppable force. The noise would be overwhelming, the ground perhaps trembling with the flow. Survivors would carry such visions in story and symbol for generations. the flood's impact on rainfall patterns was not limited to the north. By interfering with the ocean's heat transport, they contributed to shifts in monsoons and other large-scale atmospheric circulations. In Africa, a weakened monsoon meant less rain inland, turning some once green areas back into desert. In Asia, shifts in monsoon strength and timing altered river flows, affecting early agricultural experiments later in the Holocene. In South America, some regions saw the opposite effect, more rain instead of less. The same floods that began as meltwater in North America may thus have contributed to wetter conditions in parts of the southern hemisphere. The consequences were global, though very uneven. Today, scientists study these ancient outbursts as both a record of past extremes and a guide to possible future risks. The Greenland ice sheet, though far smaller than the ancient Laurentide, is melting rapidly in our warming world. If large amounts of its fresh water reach the North Atlantic, they too could influence the thermohaline circulation, perhaps not in a single cataclysmic burst, but as a persistent accumulating force. The story of Lake Agassiz and the Younger Dryas stands as a reminder that the cryosphere and the oceans are tightly linked, and that their combined effects can transform the entire climate in surprisingly short times. What makes this story especially striking is not simply the magnitude of the floods, but their speed. Earth's systems do not always adjust slowly. They can respond in sudden jumps when thresholds are crossed and barriers fail. For people at the time, those jumps were lived as stark before and after contrasts in their daily environment. For us, with satellites and models, they show up as abrupt steps and graphs and as warning signs of how quickly our own systems might change if pushed too far. In this way, the floods that helped trigger the Younger Dryas carry more than sediment to the sea. They carry lessons about the power of abrupt change, about the interconnectedness of land, ice, ocean, and air, and about how events that begin in one corner of the world can reshape the fate of all who live upon it. Among all the proposed triggers for the Younger Dryas, none has sparked as much fascination and controversy as the idea that it was initiated by something from beyond Earth, a comet or asteroid. The so-called impact hypothesis suggests that around 12,800 years ago, a fragment of a comet or another celestial body entered Earth's atmosphere over North America, exploded high above the ground, and unleashed enough energy to ignite massive fires, disturb ice sheets, and tip the climate into a 1,000-year cold spell. It is an explanation that sounds almost mythic. Fire from the sky, sudden catastrophe, and a world thrown into upheaval. Yet some scientists argue that physical evidence points in this direction. Across dozens of sites in North America, Europe, and parts of the Middle East, researchers have identified a thin layer of sediment that corresponds in age to the onset of the Younger Dryas. Within this narrow band, they report microscopic spherules of melted rock, grains of minerals formed at very high temperatures, and unusual carbon fragments that resemble the products of intense combustion. In certain locations, platinum levels spike a metal often associated with the extraterrestrial materials. To those who support the impact hypothesis, these features resemble a fingerprint of a cosmic event. They propose that a comet fragment, perhaps several kilometers across, entered the atmosphere at high speed and disintegrated in an enormous airburst, similar to the Tunguska explosion, but on a much greater scale. Instead of a single solid impact crater, the event would have produced multiple fireballs, shockwaves, and widespread heating. Forests and grasslands across broad regions could have ignited almost simultaneously. Smoke and soot would have filled the atmosphere, dimming sunlight and cooling the surface. If parts of the remnant body or its shockwaves struck ice sheets, they might have destabilized them, causing additional meltwater floods. Such an event, they argue, could help tie together several observations: abrupt cooling, extensive fires, the disappearance of the Clovis culture in North America, and the rapid extinction of many large animals there. In this view, the Younger Dryas marks not just a climatic turning point, but also a moment of planetary impact. However, this idea remains highly controversial. Many scientists are skeptical, pointing out that the evidence is far from conclusive. The microscopic spherules and other impact-like markers are not found consistently at all proposed Younger Dryas boundary sites, and some studies have failed to replicate earlier results. Certain particles once thought to be unique to cosmic impacts can form in volcanic eruptions or even in intense wildfires. Elevated platinum levels might arise from processes within Earth's crust, not just from space rocks. The argument over nanodiamonds' tiny diamond-like structures said to be present in the boundary layer has likewise swung back and forth, with some teams reporting them and others not. Perhaps the most glaring challenge to the impact hypothesis is the absence of a confirmed crater of the right age and size. Large impacts that alter global climate typically leave unmistakable scars, as the Chicxulub crater does for the event that ended the age of the dinosaurs. Supporters of the Younger Dryas impact idea counter that an airburst like Tunguska would not necessarily leave a crater. But critics respond that the scale of destruction required to trigger a 1,000-year climatic event should have left more obvious traces than we have yet found. As new studies accumulate, the scientific community remains divided. Some research bolsters elements of the impact scenario, while other work undermines or questions them. For now, the cosmic trigger remains a hypothesis rather than a widely accepted explanation. Even if it ultimately proves incorrect, the impact hypothesis has opened a valuable line of inquiry. How vulnerable is Earth's climate to external shocks? We know that very large impacts can be catastrophic. Witness the end Cretaceous event 66 million years ago. But the Younger Dryas, if impact-driven, would suggest that even smaller extraterrestrial events might destabilize climate systems that are already near tipping points. A world in which ice sheets are melting and circulation patterns are fragile might be especially susceptible to such a kick. For the people of the Younger Dryas, an airburst or impact would have been incomprehensible. Imagine seeing a brilliant streak of light grow in the sky, then explode with a flash and a thunderous roar that shattered trees and flattened animals. The blast of heat and wind could ignite fires, topple forests, and send shockwaves across the land. Survivors might have experienced what felt like the end of the world. Skies darkened by smoke, crops and wild plants burned, game animals dead or scattered. Such an event would surely give rise to powerful stories, passed from parent to child, stories of flames descending from heaven, of divine anger, of a world nearly destroyed and painfully reborn. Whether or not the Younger Dryas truly began with a visitor from space, the very possibility highlights the range of forces that can influence climate. The climate system is not closed. It is exposed not only to internal variations in oceans, ice, and atmosphere, but also to occasional jolts from beyond. Our planet travels through a solar system filled with debris, and impacts large and small have occurred throughout Earth's history. Most are inconsequential, but a few have altered the course of life itself. In the end, the Younger Dryas impact hypothesis might be confirmed, modified, or discarded as evidence accumulates. Either way, the underlying climate event remains. The world did cool abruptly, fires did burn widely, large animals did disappear, human cultures did transform. The impact idea, with its vivid narrative, may or may not belong in the final explanation. But it has sharpened our awareness that even as we study the oceans, ice sheets, and atmosphere, we must not forget the influence of the cosmos itself. Today, as we contemplate our own climate future, the Younger Dryas suggests another sobering thought. Ancient peoples could do nothing to prevent an impact or to stop massive floods once they began. They could only adapt afterward. We, by contrast, are now the primary force driving climate change. That gives us both power and responsibility. Whether or not a comet once ignited the fires of the Younger Dryas, we know that our own actions are currently heating the world. The Younger Dryas reminds us that abrupt climate shifts are possible and that their consequences can reverberate for millennia. And so, the impact hypothesis remains an open doorway in the story, a possibility that links fire from the sky to ice on the ground, and that underscores just how many threads run through the tapestry of climate. Whether the Younger Dryas was set in motion by a comet, a flood, a volcano, or some combination of all three, the lesson is the same. The climate system is sensitive and sudden shocks, whatever their origin, can change the world. If the Younger Dryas is remembered above all for its cold, it is also marked by signs of extensive fire. Across the world, in thin geological layers that correspond to the onset of this long freeze, there are traces of intense burning. Charcoal fragments, soot particles, and chemical fingerprints of combustion. These appear in lake sediments, in soils, and in ice cores taken from Greenland. Whatever initiated the Younger Dryas, it seems to have been accompanied or quickly followed by a sharp increase in wildfires, some of them on a vast scale. Evidence from North America shows sudden spikes in charcoal and lake and river sediments dating to around 12,800 years ago. Similar patterns are seen in parts of Europe and the Middle East. In Greenland, tiny particles of soot are trapped in the ice, carried by winds that must have transported smoke thousands of kilometers. For scientists, the puzzle is not whether fires occurred, but why they were so widespread and intense at this particular moment. One explanation, again, ties back to the possible impact scenario. A large airburst, or series of impacts, could have showered Earth's surface with hot debris, ignition sparks, and shock waves, setting forests and grasslands ablaze over enormous areas. In this picture, the charcoal-rich layers at the Younger Dryas boundary are the remains of those firestorms. The soot and smoke rising into the stratosphere would then contribute to cooling by blocking sunlight, a kind of impact winter that could help trigger or deepen the Younger Dryas cold. But even without invoking a comet, there are more terrestrial ways to account for the fires. As the climate warmed before the Younger Dryas, forests had expanded into areas that had previously been tundra or steppe. This expansion increased the amount of burnable material fuel across the landscape. If the climate then shifted toward drier or more variable conditions, those newly established forests might have become prone to large wildfires. A combination of longer dry spells, more frequent lightning, and perhaps human use of fire for hunting or land management could have lit the spark. Once started, fires in these fuel-rich forests would have been far more extensive than those in sparser grasslands. Volcanic eruptions could also have contributed. Eruptions often ignite fires nearby and release ash that mixes with soot from other sources. While no single known eruption perfectly matches the timing and scale needed to explain the global pattern alone, a combination of smaller eruptions and climate stressors could have created the conditions for widespread burning. Regardless of their ultimate cause, the consequences of such firestorms would have been severe. Smoke would have dimmed the skies and worsened air quality over huge areas. Ash and charred debris would have blanketed the ground, smothering vegetation and clogging waterways. Animals trapped in fire paths would have perished in large numbers, while others would have been displaced into unfamiliar regions, potentially bringing them into greater competition with humans. For human societies, fire could destroy settlements, stored food, and favored hunting grounds overnight. Imagine living in a small encampment near a forest edge and seeing flames racing toward you, driven by strong winds. The air grows hot and thick. Sparks fall like rain. The animals you depend on flee or are consumed. In the aftermath, a blackened landscape stretches out where once there had been shade, fruit, and game. People would have to move to find new sources of food and shelter, and to cope with a changed environment. Ecologically, fires can both devastate and renew. In the short term, they kill trees, burn soils, and disrupt habitats. Over longer timescales, they can stimulate the growth of fire-adapted plants and create mosaics of different habitat types. In the Younger Dryas, repeated or unusually intense burning may have pushed some forests into long-term decline, replaced by grasslands or shrublands that changed local climates further. With fewer trees to anchor the soil, erosion and dust storms could become more frequent, feeding back into atmospheric changes. For humans, these changes were both threats and opportunities. On the one hand, burned forests meant the loss of timber and firewood, as well as many edible plants. On the other hand, new grasslands attracted grazing animals, which could provide hunting opportunities. Some groups may have learned to use fire deliberately to manage landscapes, burning areas to encourage certain plants, or to drive game, an early form of ecosystem engineering. Culturally, fire would have loomed large in stories and rituals. Surviving a great fire is a powerful experience. Its memory would likely be retold as a cautionary tale, a moral lesson, or a spiritual warning. Myths of worlds destroyed by flame, of punishments raining from the sky, or of renewal through burning may all contain echoes of ancient firestorms. Combined with memories of ice and flood, these stories could form complex narratives of destruction and rebirth that shaped how communities understood their place in the world. Dust, which often follows in the wake of fires, was another imprint of the Younger Dryas. With vegetation stripped away, soils were more easily lifted by strong winds. Layers of fine sediment, known as loess, accumulated in many regions. These dust storms would have been more than a geological curiosity. They would have been a regular, tangible presence. Dust in the lungs, grit in the eyes, hazy horizons. Dust can cool the planet by reflecting sunlight, further reinforcing a cooler, drier climate. It also affects where nutrients are delivered, potentially fertilizing some ecosystems while impoverishing others. Taken together, cold, fire, and dust may have created a powerful feedback loop. Climate stress made forests more vulnerable, fires removed vegetation and produced soot. Soot and dust altered the atmosphere and the solar energy reaching the surface, reinforcing climatic shifts. This interlocking set of processes may help explain why the Younger Dryas lasted as long as it did. Once the system tipped into this fire and ice state, it took centuries for it to unwind. For human communities, navigating this world required extraordinary adaptability. They had to read not only the seasons, but also the signs of drought, the patterns of smoke on the horizon, and the shifting distribution of animals and plants. They refined technologies for warmth, shelter, food storage, and mobility. They deepened social bonds and networks of exchange to buffer against local shortages. The Younger Dryas was a test not only of physical resilience, but also of social and cultural ingenuity. When scientists today study charcoal layers in sediments or soot in ice cores, they are, in a sense, reading the traces of real, lived experiences: smoky skies, burning forests, and the uneasy aftermath that human eyes once witnessed directly. The Younger Dryas is often described as a time of ice, but it was equally a time of flame, a period when the world seemed to freeze and burn at the same time. As the centuries of the Younger Dryas unfolded, generations came and went under these challenging conditions. People learned, adapted, and told stories, carrying forward memories of ice, flood, fire, and dust. By the time the climate finally warmed again, those memories had become part of cultural identity lessons embedded in myth and tradition. And when warmth did return, it was these survivors, tempered by hardship, who stepped into the more stable world of the Holocene and began to shape the civilizations to come. By the time the Younger Dryas began, humans had already reached nearly every habitable region on Earth. They had endured the harshest phases of the Ice Age, adapted to new landscapes as ice retreated, and learned to take advantage of the opportunities created by a warming world. In the Near East, just before the cold returned, a distinctive culture had emerged. Archaeologists call these people the Natufians. They lived in what is now Israel, Palestine, Jordan, Syria, and Lebanon, a region that forms part of the Fertile Crescent, a broad arc of land known for its early role in agriculture. The Natufians are remembered not just for their tools or their ornaments, but because they stand at a crucial turning point in human history. They were among the first people to take clear steps toward what would become farming. Before the Younger Dryas, the Natufians thrived in a landscape that was becoming more generous year by year. Wild cereals, ancestral forms of wheat and barley grew in thick stands across the hills and valleys of the Levant. These plants were not yet domesticated, but they produced heavy clusters of grain that ripened in the warm season and could be gathered with simple tools. The Natufians developed flint sickle blades to cut these grasses and stone mortars and pestles to grind the seeds into flour. Unlike many of their contemporaries, they began to construct relatively permanent houses, often circular structures built of stone, with hearths at their centers. Villages of dozens, sometimes hundreds of people began to appear. These were among the first truly sedentary communities in human history. Such a shift was possible because the environment offered a rare degree of reliability, abundant wild grains, plentiful game, and relatively stable water sources from springs and streams. With food within reach, the Natufians no longer needed to follow herds constantly. They could store grain, dry meat, and invest in buildings meant to last beyond a single season. They also buried their dead in organized cemeteries, often with beads, shells, and other adornments. This suggests a rich, symbolic life, with traditions and beliefs that extended beyond daily survival. Surplus food likely allowed them more time for ritual, art, and the strengthening of social ties. Their world was moving toward greater complexity, grounded in the stability of a warming climate. Then the Younger Dryas arrived, and that stability was shaken. The sudden return of cold and greater climatic variability upset the delicate balance that the Natufians had begun to depend on. Wild cereals that had once ripened reliably became less predictable. Shorter, cooler growing seasons and changes in rainfall meant that stands of wild barley and wheat sometimes failed to mature. Herds of gazelles and other game animals shifted their ranges in response to new vegetation patterns, making them harder to find. Springs and smaller streams could dry out more often in prolonged droughts. The same landscapes that had supported permanent villages now became unreliable. For many Natufian communities, the only feasible response was to move. Archaeological evidence shows that some previously large, stable settlements were abandoned, and people returned to more mobile ways of life, moving seasonally to follow resources, as their ancestors had done for thousands of years. Stone house foundations become less common, and settlements tend to shrink in size and permanence, reflecting a retreat from the sedentary experiment. Yet not all Natufians responded in the same way. In some areas, rather than giving up on cereals altogether, groups began to manage them more actively. If wild stands no longer ripened dependably in distant fields, perhaps they could be encouraged to grow closer to camp. Perhaps seeds could be scattered in particular soils, weeded, or protected, so that the plants would be more likely to produce a harvest even in difficult years. Over time, such tinkering would lead people to notice which plants yielded better, which seeds were easier to harvest, and which strains survived the cold. Those seeds would be saved and sown again, beginning a slow process of selection. From this perspective, the Younger Dryas did not halt the move toward agriculture. It intensified it. Under the pressure of scarcity, some Natufians shifted from simply gathering what grew on its own to trying to control and improve their plant resources. They could no longer rely on nature's generosity. They had to shape it. In this way, one of the greatest revolutions in human history, the agricultural revolution, may have been accelerated not by abundance, but by crisis. Archaeological sites from this period provide tangible clues. At places like Jericho and other early settlements in the region, we find grinding stones, sickle blades with a glossy sheen from repeated cereal harvesting, and storage pits designed to hold grain. Some seeds from these sites show early signs of domestication, changes in size and in the way the grains attach to the stalks, indicating human selection. These plants were not yet identical to modern crops, but they were on their way, guided by human hands through successive generations. The Natufians also left evidence of shifting social patterns. Some burials become more elaborate, with individuals interred alongside beads, animal bones, and carefully crafted tools. In several cases, dogs were buried together with humans, signaling one of the earliest known examples of close human-dog companionship. These animals were likely used for hunting and protection, but the care shown in their burial suggests a deeper emotional and symbolic bond. Under the stress of a harsher climate, partnerships with other species dogs, and eventually goats and sheep, became ever more central to survival. Exchange networks appear to have persisted, or even strengthened. Obsidian from distant Anatolian sources, shells from the Mediterranean coast, and other non-local materials show up in Natufian sites, indicating long-distance contacts. In a time of scarcity, such networks could act as safety nets. If one community suffered a poor harvest or a drop in game, others might help supply what they needed, with the understanding that the favor could be returned later. In this way, social connections became as important as technological innovations in weathering the Younger Dryas. It is crucial to remember that the shift to agriculture was not a single event or a clean break from foraging. It unfolded gradually over many generations. The Younger Dryas did not cause farming in a simple, linear way, but it created circumstances in which people were more motivated than ever to experiment with cultivation. By the time the climate warmed again and the Holocene began, much of the knowledge needed to farm how to sow seeds, tend fields, store harvests, and manage herds was already in place. In this sense, the Natufians occupy both sides of a historical threshold. They show us what was lost when the Younger Dryas struck: permanent villages, dependable wild harvests, and a sense of environmental stability. But they also show us what was gained: the first deliberate efforts to tame plants and animals, the beginnings of domestication, and a level of resilience and creativity that would carry humanity into a new era. Their story is one of adaptive choice in the face of adversity. Either return fully to older ways of life, or push forward into new ones. That choice helped set the course for everything that followed. When we look at farming today, it can be easy to think of it as inevitable, as though humans were always destined to invent agriculture, build cities, and develop complex societies. The Natufian story reminds us that this path was not preordained. It emerged through a series of responses to environmental stress. Without the Younger Dryas, the move from foraging to farming might have taken a very different path, or might have been delayed by centuries or millennia. Faced with cold, drought, and scarcity, the Natufians and their neighbors took crucial steps toward a radically different way of life. So as the Younger Dryas froze rivers and shortened growing seasons, the Natufians responded in two broad ways. Some left their villages and moved more often, tracking game and wild plants across the land. Others stayed and experimented, working with seeds and soil in new ways, and in doing so, laying the groundwork for agriculture. From hardship, they drew innovation. From instability, they sought control. From the long freeze, they helped ignite the first sparks of farming. When the Younger Dryas settled in, no community on Earth was completely untouched. The sudden return of cold and the shifts in rainfall forced people everywhere to make choices about where to live, what to eat, and how to adapt. Some chose movement, abandoning marginal territories for more favorable ones. Others stayed put but reshaped their diets, technologies, and social structures to fit the new reality. What emerges from the archaeological record is not a story of universal collapse, but one of resilience, migration, and creativity under pressure. For hunter-gatherer groups in Europe, the cooling pushed forests back and restored tundra landscapes. Animals that thrived in cold, such as reindeer and wild horses, became more central again. Hunters followed their migrations, altering their seasonal rounds and honing techniques for tracking and capturing swift-moving prey in open country. At the same time, smaller mammals, fish, and birds became increasingly important food sources. Archaeological sites display changing bones in their refuse heaps, reflecting a broader spectrum of animals being captured and consumed. To survive, people had to be opportunistic and flexible in what they considered food. In the Near East, where Natufian communities had begun experimenting with sedentary life, survival meant weighing difficult options. For some, mobility once again offered the best chance, allowing them to chase shifting resources and avoid overtaxing any one location. For others, staying in place and investing more in managing plants and animals seemed worth the risk. Both strategies came with costs and benefits, and both represent different ways of engaging with an unpredictable environment. Migration was a central response across many regions. As climates shifted, entire landscapes changed in their capacity to support human life. In North Africa, parts of the Sahara had been greener during the earlier warming period, with patches of grassland, lakes, and wetlands supporting pastoral and foraging groups. As the Younger Dryas progressed, those areas dried again. People who had moved into these promising zones were forced to retreat toward the Nile Valley, where the river's steady flow offered a more stable water supply. The concentration of populations along this narrow, fertile corridor would, much later, provide the foundation for complex societies in ancient Egypt. In Europe, some groups drifted southward as northern regions grew too harsh, while others lingered at the edges of ice and tundra, following the cold-loving herds. To move was not always a free choice. In many cases, hunger compelled it. A failed hunting season, a dry year with poor plant yields, or the disappearance of a key animal species from a territory could force entire bands to relocate, sometimes bringing them into contact and conflict with other groups. Adaptation took place not only in where people lived, but in how they lived together. As resources grew more uncertain, cooperation became more valuable. Groups likely strengthened internal bonds and sometimes formed new alliances with neighbors. Archaeological evidence shows that trade in raw materials such as obsidian, flint, and shells continued through the Younger Dryas, and in some areas, it may have increased. These exchange networks were not simply about luxury goods. They helped communities spread risk. Information, too, was a critical form of exchange. Knowledge of where herds had moved, where water could still be found, or which plants remained reliable in tough conditions. At the same time, scarcity could fuel competition and conflict. Migration into inhabited territories meant that different groups occasionally competed for the same game: waterholes or plant-rich valleys. Skeletal evidence at some sites hints at interpersonal violence or warfare. Survival strategies in the Younger Dryas thus encompassed both cooperation and confrontation, with human responses as complex as those we see in times of crisis today. Technology evolved in parallel. In North America, after the decline of the Clovis culture, new projectile points and hunting tools emerged, smaller, more efficient, and often better suited for hunting smaller animals or fishing. In Europe, tiny stone blades called microliths became common. These could be set into wooden or bone shafts to make composite weapon spears, arrows, or barbed points that were lightweight and versatile. In the Near East, grinding stones and mortars became more numerous, reflecting increased reliance on plant foods like seeds and nuts. Each innovation represented a tactical response to new challenges, adjusting tools to the resources available. Knowledge passed between generations played a critical role. In a world where environmental baselines were shifting, memory of past conditions could help guide decisions. Elders might recall where water remained in drought years, which valleys still harbored animals during severe winters, or which plants provided fallback foods when preferred ones failed. Oral stories, tales of past hardships, of strange weather, of journeys likely encoded practical wisdom within narrative. By embedding lessons in myth and ritual, communities ensured that crucial information could outlive individual memories. Even under such pressure, people continued to create meaning beyond basic survival. Art, music, and ritual life did not stop. Cave paintings, decorated tools, carved figurines, and arranged stones from the Younger Dryas show that symbolic and aesthetic expression remained important. These cultural practices may have become even more vital in hard times, strengthening group identity and offering comfort and continuity when the environment felt unpredictable. Shared rituals might have helped communities process loss, mark seasonal changes, or reaffirm hope. For many, the Younger Dryas would have defined the boundaries of the possible. Children born into its cold and scarcity would grow old without ever knowing a different climate. They might hear stories from their grandparents of a slightly warmer world with more abundant forests. But to them, those accounts might have sounded almost like legends. Migration, adaptation, and risk management were not emergency responses. They were the fabric of everyday life. In retrospect, we can see that the strategies honed during the Younger Dryas were pivotal. The turn toward farming in the Near East, the dietary diversification in Europe, the reorientation of hunting practices in North America. These were all shaped directly by the pressures of the cold period. When the climate finally warmed, these adaptive innovations did not disappear. Instead, they provided the foundation for taking advantage of the Holocene's relative stability. Without the survival strategies forged in the freeze, humanity might not have been prepared to build the larger, more settled societies that followed. Thus, the Younger Dryas stands not only as a story of hardship, but also as a demonstration of human ingenuity. People did not simply endure, they changed how they lived. Migration widened their geographical horizons. Toolmaking grew more sophisticated, social networks deepened. In the crucible of a 1,000-year winter, resilience became not just a trait, but a way of life. So, while the Younger Dryas shortened summers, froze rivers, and forced people away from familiar lands, it also set in motion significant transformations. Movements created new connections among distant groups. Adaptations fostered new technologies and new relationships with plants and animals. Survival under such conditions demanded flexibility, and from that flexibility came many of the traits that would later allow civilizations to flourish. When the Younger Dryas finally ended more than 11,000 years ago, it did so without leaving a written chronicle. The people of that time had no alphabets or scripts with which to record their experiences, yet they had words, stories, rituals, and songs. For as long as humans have existed, we have told one another about events that shaped our lives, disasters, wonders, times of plenty and of fear. Over generations, those accounts often became myths, layered with symbolism but still carrying the memory of real happenings. Across cultures today, one of the most common mythic themes is the Great Flood. Stories from Mesopotamia, India, the Mediterranean, the Americas, and Oceania tell of waters rising suddenly, of deluges swallowing land, of survivors clinging to mountaintops or boats. These tales may reflect a deep, shared experience, the catastrophic floods that accompanied the end of the last ice age and the Younger Dryas. As glacial lakes burst, rivers swelled, and seas rose, people would have seen valleys inundated and coastal lowlands disappear. To watch a homeland drown beneath advancing waters would be unforgettable. Passed on through countless retellings, those memories could easily transform into enduring flood myths. Fire appears just as prominently in traditional stories. Myths of fire raining from the sky, of worlds burned and remade, of divine punishment through flames, can be found across continents. If the Younger Dryas was indeed accompanied by immense firestorms, whether sparked by an impact, climate stress, or both, then survivors would have had powerful reasons to remember them. Skies filled with smoke, forests turning to ash, animals and people caught in infernos. Such experiences are likely to live on in culture long after the details of their physical causes are forgotten. Over time, the raw memory of disaster may have been reshaped into narrative, framed as punishment, cleansing, or the turning of a cosmic cycle. Cold itself also finds echoes in oral traditions. In northern latitudes, folklore often includes tales of unending winters, failing suns, or times when frost devours the world. In Norse mythology, recorded much later but rooted in older oral traditions, there's the idea of Fimbulwinter, a great winter that precedes the world's end. While we cannot link such myths directly to the Younger Dryas, they resonate strongly with the idea of a prolonged, brutal cold spell that reshaped life for many generations. In North America, some indigenous stories speak of giant animals that once roamed the land, enormous mammoths, great sloths, fearsome predators that no longer exist. These may preserve faint recollections of megafauna that disappeared around the time of the Younger Dryas. The discovery of ancient bones in riverbanks and eroding hillsides would have reinforced these tales, providing tangible proof that such giant creatures had indeed been real. The extinction of these animals was not only a biological event but also a cultural one, altering how people imagine the world's past and their place within it. Myths are not literal records. They change as they are told and retold, shaped by each generation's needs and worldview. Yet at their core, many seem to encode genuine experiences. Floods that erased familiar landscapes, fires that blackened the sky, winters that seemed to have no end, and the disappearance of animals that had once been central to daily life. When anthropologists and geologists compare oral traditions with physical evidence, they often find surprising alignments. A legend about a great wave may correspond to a known tsunami. A story about fire from above may echo a meteor airburst. The myths of the Younger Dryas era, though transformed over thousands of years, may still be with us in this way. For the people living through the Younger Dryas, myth served vital functions. It offered explanations for the inexplicable. Why had the world grown so cold again? Why had favored animals vanished? Why had waters risen and lands burned? In the absence of scientific frameworks, stories about gods, spirits, or cosmic forces provided answers and helped people cope with events beyond their control. Myths also functioned as warnings. Tales of floods might teach communities to respect rivers and coasts. Narratives of fire from the sky might encourage vigilance and humility. Stories of endless winter might instill the importance of preparation and of caring for one another in hard times. Even now, we can sense the resonance of these ancient patterns. The story of Noah's flood, the Mesopotamian account of Utnapishtim, the Hindu tale of Manu, indigenous American stories about previous worlds destroyed and remade, all share common themes: overwhelming destruction, divine or cosmic intervention, and the survival of a remnant who must rebuild. While each tradition developed in its own cultural and historical context, it is compelling to imagine that some of these narratives preserve dim recollections of Ice Age and post-Ice Age catastrophes, including those associated with the Younger Dryas. The Younger Dryas also highlights how myth and science can complement one another. Science reconstructs the physical events, using ice cores, sediments, fossils, and models to understand how temperatures changed, where floods flowed, which animals died out, and when. Myth preserves the human perspective, what it felt like to see familiar lands vanish, to mourn lost creatures, to endure in the face of forces far beyond human power. Each perspective is incomplete without the other. Together, they paint a richer picture of what such a climate upheaval really meant for those who lived through it. Science can tell us that Lake Agassiz drained in massive outbursts, raising sea levels and flooding valleys. Myth can imagine how it felt to see the waters rise, to lose a homeland, to cling to rafts or high ground, and to start life over in a changed world. Science can identify a sudden cooling. Myth can capture the dread and awe of a winter that seemed never to end. In both cases, the underlying message endures. The world can change quickly, and survival depends on adaptability and memory. In a sense, the Younger Dryas still speaks through those old stories. We may not know exactly what words were used around ancient campfires, but we hear their echoes in today's legends of destruction and renewal. They remind us that people long ago were not merely passive victims of climate. They were observers, interpreters, and storytellers, just as we are. As the Younger Dryas tested human communities with cold, drought, flood, and fire, it also fostered a powerful tradition of storytelling. Those stories endured long after the ice retreated, passed down from elders to children, woven into rituals, and transformed into myths. They continue to whisper to us when we hear tales of sunken lands, of worlds set aflame, of beasts that once walked the earth, and of new beginnings after great loss. For more than 1,000 years, Earth remained in the grip of the Younger Dryas. Winters were long and unforgiving, summers were brief and often cool. Rainfall patterns had shifted, and people across continents had adapted their ways of living to this reality. By the time the cold lifted, many generations had lived and died knowing nothing else. To them, this climate was normal. Then, almost as swiftly as the cold had come, it ended. Greenland's ice cores, those frozen chronicles of past weather, show an astonishing transition. Around 11,700 years ago, temperatures in Greenland jumped by as much as 10 degrees Celsius in only a few decades, perhaps even faster. In climate terms, such a change is nearly instantaneous. One moment, the planet hovered in the last breath of the Ice Age. The next, it entered the warmer, more stable state we call the Holocene. What caused this abrupt termination remains as puzzling as the Younger Dryas' onset. The leading theory once again involves the Atlantic circulation system. If the Younger Dryas was sustained by a weakened or stalled thermohaline circulation due to fresh water, then the end of large meltwater inputs. Either because ice sheets had shrunk or because major lakes had already drained, could have allowed salinity in the North Atlantic to recover. Once the surface waters were salty and dense enough to sink again in large volumes, the circulation could restart, and warm water would surge back toward the north. That renewed flow of oceanic heat would explain the sudden warming recorded in Greenland and much of the North Atlantic region. Another possibility is that the climate system itself crossed an internal threshold. Perhaps the Younger Dryas represented one stable state of the system, and as background conditions slowly shifted through changes in Earth's orbit, greenhouse gas levels, and ice extent, it eventually became unstable. The system then flipped rapidly to a different state, the warm Holocene, without needing a singular external trigger. In this view, the Younger Dryas ended not because of one final catastrophic event, but because the climate could no longer sustain that configuration. Whatever the underlying mechanism, the effects were profound. Forests began to surge northward again. Within a few centuries, formerly open tundra was overtaken by trees. In Europe, pollen records show swift increases in species such as oak, elm, and hazel. Reindeer and other cold-adapted animals retreated to higher latitudes and altitudes, while deer, boar, and other temperate animals expanded into newly wooded areas. Rivers flowed more consistently as precipitation patterns stabilized and glaciers shrank. Lakes refilled and grew more productive, supporting fish and bird populations. The world was no longer a place of constant scarcity. In many regions, it became a place of growing abundance. For human societies, the transition was nothing short of transformative. Communities that had been forced into high mobility now found that certain regions became reliably rich in resources year after year. Plants grew more predictably. Animal ranges stabilized. In the Near East, the early agricultural experiments that had begun under Younger Dryas stress could now flourish in a more forgiving climate. Wild cereals that had struggled during the cold period once again ripened in abundance. Combined with already developing cultivation practices, this allowed for the rise of fully agricultural societies in the Fertile Crescent. Villages grew larger and more permanent. At sites like Jericho, we see increasingly substantial structures, defensive walls, and communal works. Food surpluses made it possible for some individuals to specialize in tasks other than food production, toolmaking, trade, or ritual leadership. Social hierarchies began to form. Within a few thousand years, these early villages would evolve into the first cities. In Europe, hunter-gatherers expanded into the newly forested landscapes, refining ways of life that took advantage of rivers, lakes, and woodlands. Fishing, nut gathering, and hunting forest game became central activities. In North America, people adjusted to the permanent loss of megafauna, focusing on deer, elk, bison, and smaller animals, as well as plants and fish. Everywhere, the end of the Younger Dryas opened up ecological niches and opportunities for human ingenuity to unfold in new directions. Yet for those alive during the actual transition, the experience must have been startling. Imagine having grown up in a world where icy winds dominated, where food was often scarce, where migration felt like a constant necessity, and then seeing within your lifetime the land grow greener, the summers grow longer, the animals become more plentiful. Trees would appear in places they had not been before. Rivers would thaw earlier in the spring and freeze later in the autumn. The sky might seem more generous. For people who had heard tales from elders about a slightly warmer past, it might have felt as though those stories were finally coming true. The timing of this shift is deeply significant. The Holocene, which began with the end of the Younger Dryas, provided the long stretch of climatic stability on which agriculture and civilization were built. Without that stable background, large-scale farming would have been difficult, and maintaining permanent cities nearly impossible. The sudden conclusion of the Younger Dryas thus marks not only the end of an Ice Age remnant, but also the opening of a new chapter in the human story. Geological and biological records capture this reawakening in various ways. Pollen cores show rapid vegetation changes. Sediments in lakes and oceans record shifts in erosion and nutrient flow. Animal bones in archaeological sites reflect changes in diets and hunting practices. Together, these archives reveal that the world after the Younger Dryas was, in many ways, a new world, different plants, different animals, and different human ways of life. The abruptness of the warming has also prompted reflection on resilience. If the climate can move so quickly from cold to warm, from scarcity to abundance, the window for adaptation can also be surprisingly short. In the case of the Younger Dryas, human societies had already developed the flexibility needed to survive climatic swings. They were able to seize the new opportunities offered by the Holocene, almost immediately expanding agriculture, building permanent settlements, and deepening trade and cultural exchange. For us today, the end of the Younger Dryas underscores the capacity of Earth's climate to change rapidly in both directions. While we are now concerned primarily with warming rather than cooling, the principle is the same. Once certain thresholds are crossed, the system can shift quickly, affecting every aspect of life. For ancient communities, the return of warmth was likely felt not as an abstract climatic event, but as a kind of rebirth. Springs flowing again, game returning, plants thriving. For them, it was a gift and a chance to rebuild, to imagine futures based on stability rather than uncertainty. Their myths and rituals may have celebrated this shift as the favor of gods or spirits, a sign that the world was once more in balance. Thus, the Younger Dryas ended not with a slow fade-out, but with a sharp pivot. One climatic regime gave way to another. The Ice Age finally loosened its grip, and Earth moved into the Holocene, the relatively gentle climate that has cradled all human civilization so far. For modern scientists, this event remains a key case of abrupt climate change. For the people who lived through it, it was likely experienced as the dawning of a new world. When the Younger Dryas came to its abrupt close, the transformation that followed was not limited to numbers on climate graphs. It was a reawakening that could be seen in every hillside, heard in every forest, and felt in every human community. For more than 1,000 years, the world had been held in a state of hesitancy and constraint. Ecosystems were lean. Human lifeways were constantly under strain. With the onset of the Holocene, that tension eased. Life, in many places, surged forward. We can see this resurgence clearly in the record of pollen grains preserved in lake sediments across Europe, the Middle East, and Asia. Before the Holocene, these sediments are dominated by pollen from grasses and shrubs. Then, suddenly, tree pollen explodes in abundance. Oak, elm, hazel, and other broadleaf species spread rapidly, replacing more barren tundra vegetation in a matter of centuries. In some areas, this shift may have been visible within just a few human generations. Children who had grown up in open, treeless landscapes might live long enough to see dense woodlands take their place. For animals, the spread of forests meant new possibilities. Species adapted to woodlands, deer, wild boar. Many bird species found expanding habitats and abundant food. Cold-loving animals like reindeer pulled back to more northerly or higher elevation refuges. In rivers and lakes, more stable flows and warmer temperatures supported thriving fish populations. Wetlands and floodplains, renewed by regular seasonal flooding rather than chaotic outburst floods, hosted diverse communities of plants and animals. The entire web of life became more intricate and productive. For humans, this meant a broader and more reliable menu. In Europe, fishing and shellfish gathering provided steady protein, while nuts, fruits, and forest game offered varied sources of calories. In the Near East, the same conditions that favored wild cereals also supported other plants useful for food and fiber. In East Asia, warmer, wetter conditions nurtured the wild ancestors of rice and millet in river valleys and lowlands. In the Americas, ecosystems reorganized in ways that would later support the domestication of crops like maize, beans, and squash, as well as the management of animals such as llamas and alpacas in the Andes. In the Fertile Crescent, the agricultural experiments that had germinated during the Younger Dryas found their true footing in the Holocene. Wild wheat and barley, once stressed by cold, now grew robustly. People who had already learned to sow seeds and tend fields intensified those practices. They built larger storage facilities, indicating larger harvests and the accumulation of surplus. Domesticated strains of crops and animals became more distinct from their wild ancestors. Goats and sheep, tamed gradually over generations, became central to many communities. With reliable food production, populations grew, and villages expanded in both size and complexity. This growth brought new forms of social organization. With surpluses, not everyone needed to participate directly in food production. Some individuals could focus on crafting tools, organizing trade, or officiating rituals. Differences in wealth and status began to appear. Burials from this period show some individuals interred with more goods than others, suggesting the early emergence of social hierarchies. Over time, these small inequalities would grow into the stratified societies of later city-states and kingdoms. Trade networks flourished in the newfound stability, Communities traded obsidian for sharp blades, exotic shells for decoration, and pigments for art. Ideas and technologies traveled along the same routes: methods of cultivation, styles of pottery, symbolic motifs, and religious concepts. The Holocene's relative climatic calm acted as a foundation on which human cultural complexity could build layer by layer. Not all regions experienced the Holocene as straightforward abundance. In some areas, the warming trend eventually led to drying rather than greening. The Sahara, for example, passed through a green Sahara phase with lakes and grasslands that supported people and animals, before gradually becoming the hyper-arid desert we know today. In other places, rising sea levels flooded coastal lowlands, displacing communities and submerging early settlements beneath the waves. Yet even in these challenging situations, people responded with the adaptive skills honed during the Younger Dryas, migrating, innovating, and reconfiguring their societies. The Earth itself continued to adjust physically. As remaining ice sheets melted, their weight on the crust lessened. Isostatic rebound continued to lift some landmasses, altering local shorelines and sometimes triggering earthquakes. Volcanic activity in certain regions increased as the crust responded to shifts in stress. In a geological sense, the planet was not simply returning to a pre-Ice Age state, it was entering a new configuration. For those alive at the time, the pace of change would have been undeniable, even without scientific instruments. Older people could point to hills now forested that had once been bare, to rivers that now flowed year-round instead of seasonally, to animals newly present in the area. The vividness of these changes would have impressed itself on memory and story. Myths of world renewal of lands reborn after catastrophe, of golden ages following dark times, may have roots in this observable transformation. At the same time, the Holocene's beginning did not erase the lessons of the Younger Dryas. Memories of scarcity, migration, and uncertainty likely persisted, quietly shaping choices about how much food to store, where to build, and how to organize society. Farming may have seemed not just an opportunity, but a safeguard against the possibility that harsh conditions could return. Rituals to honor deities of weather, fertility, and harvest may reflect an underlying awareness that the climate, though now stable, could never be fully controlled. As a result, the Holocene reawakening was both an ecological and a cultural transition. Ecologically, life rebounded and diversified. Culturally, humans moved from primarily mobile, small-scale societies toward increasingly settled, larger, and more complex ones. They began to create enduring structures, not only houses, but monuments and communal spaces. At sites like Göbekli Tepe in modern Turkey, people erected massive stone pillars carved with animals and symbols, likely used for gatherings and rituals on a scale unseen before. Such projects suggest high levels of coordination, surplus resources, and shared beliefs. They stand as early markers of what would become large, organized societies. From a modern vantage point, it is tempting to see the end of the Younger Dryas and the dawn of the Holocene as the birth of the world we know. It was then that the foundations of agriculture, urbanization, and long-distance trade were laid. Yet this birth was built on the resilience and ingenuity developed during the long freeze. The same capacity to adapt that carried humans through the Younger Dryas now enabled them to thrive in the new, warmer conditions. Looking back, we can say that the reawakening following the Younger Dryas was not simply a return to normal. It was the beginning of a new normal, one in which human societies would increasingly shape their environments rather than merely respond to them, and in which the seeds, literal and figurative, of civilization were sown in soil enriched by both hardship and opportunity. As the Younger Dryas faded and the Holocene took hold, humans did not simply settle back into their old roles as hunters and gatherers. Something new had begun. For countless generations, people had relied on wild plants and animals, managing to survive through flexibility and deep knowledge of local ecologies. The Holocene's relative stability now allowed them to move further along a different path, the path of cultivation and domestication. The central ingredient was reliability. During the Younger Dryas, wild plant and animal populations had fluctuated erratically, undermining any long-term dependence on a narrow range of resources. In the early Holocene, seasons and rainfall patterns became more predictable. Plants tended to ripen on schedule. Animals followed consistent breeding cycles and migration routes. This predictability opened the door to planning. People could plant seeds with reasonable confidence that they would sprout. They could invest labor in building permanent homes or storage structures, knowing they were likely to be able to refill them. They could coordinate community efforts around sowing and harvest times that more or less repeated each year. In the Fertile Crescent, the wild precursors of wheat and barley were perfectly positioned to be taken into human hands. People had already learned how to harvest and process them during the Natufian period. Now, as they sowed the seeds closer to their homes and deliberately cultivated them, the plants began to change. Over many generations, grains with certain traits, larger size, stronger attachment to the stalk, more synchronous ripening, were unintentionally favored because they were easier to harvest and produced better yields. Gradually, the cereals of the fields became genetically distinct from their wild ancestors. These new plants depended on humans for their propagation, just as humans increasingly depended on them for food. Parallel processes unfolded with animals. Goats and sheep, once targeted primarily as prey, were drawn into closer relationships with people. Young animals might be captured and raised near camps, providing an accessible store of meat, milk, and hides. Over time, humans began managing breeding, favoring animals that were less aggressive, more productive, or more tolerant of human presence. These early herding practices transformed once wild creatures into domesticated livestock. Dogs, domesticated even earlier, became even more central, not only as hunting partners, but as guards and companions in settled communities. As plant cultivation and animal herding expanded, permanent settlements grew more common and more complex. Villages in the Fertile Crescent became larger and more densely populated. Houses clustered together, often with shared storage areas and communal facilities. At Jericho, thick stone walls and a remarkable stone tower among the earliest large-scale architectural works in the world suggest the presence of organized labor and shared goals, possibly for defense or for ritual. These were no longer small, temporary camps, but enduring places shaped by generations. Surplus production of food brought profound social consequences. When harvests were good, communities could store grain to carry them through lean periods. Surpluses also meant that not every person needed to be directly involved in food acquisition. Some could specialize in other tasks, crafting pottery, working stone or metal, organizing trade expeditions, or leading religious ceremonies. Such specialization marked the beginning of more intricate social structures. Over time, roles and statuses diversified, and new forms of power and inequality emerged. As agriculture took root in the Fertile Crescent, similar developments appeared independently in other parts of the world. In the river valleys of China, millet and rice were domesticated. In Mesoamerica, people began cultivating maize, beans, and squash. In the Andes, tubers like potatoes and grains like quinoa were domesticated alongside pastoralism with llamas and alpacas. In sub-Saharan Africa, sorghum and yams entered into human care. Each region's path to agriculture was shaped by local species and conditions, but all shared the same fundamental shift, from relying on what landscapes spontaneously offered, to actively reshaping those landscapes to provide predictable yields. This global flowering of agriculture did not happen all at once, nor did it eliminate hunting and gathering. For long periods, many communities mixed strategies, farming some crops, herding some animals, while still hunting, fishing, and foraging when possible. Yet the long-term trend was clear. As population densities increased and as fields and herds became central to survival, more and more societies oriented themselves around agriculture. That orientation would eventually lead to the rise of cities, states, and empires. Culturally, these changes had far-reaching effects. Farming ties people to specific pieces of land, strengthening territorial identities and connections to place. Sacred groves, fields, and hills became important in spiritual life. Early temples and communal ritual sites arose, reinforcing shared beliefs and legitimizing social structures. Göbekli Tepe, with its monumental stone circles, appears to have been built by hunter-gatherers on the threshold of farming, but similar gathering places would later be integrated into fully agricultural societies. Religion, governance, and economy became more tightly intertwined as communities grew. Health and lifestyle also shifted. Farming provided more stable food supplies than hunting and gathering, but often at the cost of dietary diversity. Early agriculturalists tended to consume more carbohydrates and fewer varied wild foods. Skeletal remains from early farming communities sometimes show evidence of nutritional deficiencies, increased workload stress on bones and joints, and higher rates of disease likely due to higher population densities and closer contact with domesticated animals. Agriculture brought security and surplus, but it also brought new vulnerabilities. Even so, the advantages of farming in a stable climate were immense. Surpluses could support larger populations and buffer communities against short-term environmental fluctuations. Stored food allowed people to plan for the future in ways that highly mobile groups could not. Over centuries, this ability to accumulate resources and invest in infrastructure, irrigation canals, terraces, defensive walls, roads, became a defining feature of many societies. Intellectually and spiritually, the shift to agriculture and permanent settlements altered how people thought about time and change. Farmers became attuned to seasonal cycles, to the rhythms of sowing and harvest. Calendars and early forms of astronomy developed in part to track these cycles accurately. Myths and rituals focused on fertility, growth, death, and rebirth, reflecting the visible transformations in fields and herds. The memory of older, more mobile lifeways persisted, but new identities emerged. People saw themselves as caretakers of land, as members of enduring communities rooted in specific places. In this broad transformation, the Younger Dryas plays a crucial role as both obstacle and catalyst. Its hardships delayed the full realization of sedentary life, but they also spurred the innovations that made agriculture possible. Once the Holocene stability arrived, those innovations could spread and intensify. It was as if humanity had been tempered by the cold, then given a warmer stage on which to apply what it had learned. The seeds of civilization were thus not only literal seeds planted in early fields, but also the ideas and social patterns cultivated during this era. Cooperation in farming and irrigation projects, systems for sharing and storing surplus, norms for dividing land and managing conflict. All of these were early forms of the complex institutions that would later define states and empires. In a quiet but decisive way, the end of the Younger Dryas and the rise of the Holocene mark the beginning of human history as we usually think of it. A story not only of survival, but of building enduring structures, physical, social, and symbolic, that could last across generations. The Younger Dryas is now long past, but it remains one of the most crucial episodes in the story of our planet and our species. It was not the coldest time humans ever endured, nor the longest lasting climate interval. What makes it so important is how abruptly it began, how profoundly it reshaped ecosystems and societies, and how rapidly it ended. It stands as the clearest example we have of how quickly climate can change, and how deeply those changes can permeate every aspect of life. From this event, several enduring lessons emerge, lessons that connect the experiences of people 12,000 years ago with the challenges we face today. One lesson is about resilience. When the Younger Dryas began, it was a shock. Communities that had begun to rely on stable patterns of warmth and rainfall suddenly found themselves back in a harsher world. Villages built around wild cereal harvests confronted failing crops. Herds changed their migration routes or vanished. Water sources dried or froze. Yet humans did not disappear. They adapted. Some moved back toward nomadic strategies, roaming widely to follow game and gather diverse plants. Others doubled down on experimentation with cultivation and animal management. Everywhere, people altered their tools, their diets, their movement patterns, and their social structures to survive. That resilience was not automatic. It was built through daily decisions about cooperation, sharing, risk-taking, and innovation. It depended on social bonds, on the ability to learn from elders, and on the willingness to change habits. The fact that our species emerged from the Younger Dryas not only alive, but in some regions stronger and more inventive, is a testament to that adaptability. Another lesson is that crises often drive innovation. The Younger Dryas did not give birth to farming in a peaceful garden paradise. Instead, it accelerated agricultural experimentation in landscapes where wild resources had become less dependable. The pressure of scarcity pushed people to plant seeds intentionally, to coop animals, and to refine techniques for storage and processing. The same stress that forced others to abandon their villages also motivated some to devise new ways of interacting with the environment. From those experiments came agriculture, and from agriculture came cities, writing, states, and much of what we call civilization. A third lesson is that climate change is global, but its effects are uneven. During the Younger Dryas, some regions froze, others dried, and some became wetter. Northern Europe and North America experienced severe cooling, while parts of the southern hemisphere saw different patterns. Monsoon systems weakened in Asia, robust lakes shrank in Africa, and rainfall increased in some areas of South America. These uneven impacts created a patchwork of hardship and opportunity. Some communities were forced to move or change, others found new niches in emerging environments. This remains true today. Our current warming will not affect all places equally. Some will face extreme heat and drought, others more intense storms and floods, others rising seas. Understanding this unevenness is critical for planning fair and effective responses. A fourth lesson is about the sensitivity of the climate system. The Younger Dryas appears to have been triggered by disruptions that, on the scale of the whole planet, might at first seem minor pulses of fresh water into a single ocean basin, or perhaps a sudden injection of particles and soot into the atmosphere. Yet these inputs were enough to stall a major circulation system and tip the world into a different climatic state. This reminds us that the climate is not a static backdrop, but a complex, interconnected system with tipping points and feedbacks. Push it too far in one direction, and it can reorganize itself in ways that are difficult to reverse. For today's world, already warming rapidly due to greenhouse gas emissions, this is a warning. We know that modern climate change is altering ice sheets, oceans, and forests. It may also be inching us closer to thresholds, such as the large-scale melting of Greenland or the collapse of parts of the Atlantic circulation, beyond which change could accelerate and become more difficult to predict or control. The Younger Dryas also underscores the importance of memory. Ancient peoples could not write down what they experienced, but they preserved it in stories, rituals, and practices. Myths about floods, fire, and endless winter allowed communities to remember and learn from past upheavals. Today, we have far more precise tools, instrumental records, satellite data, and carefully dated cores of ice and sediment. But we still face the same challenge: to remember and act upon what we know. Forgetting the lessons of past climate events is one of the surest ways to repeat their most damaging patterns. Finally, the Younger Dryas teaches that abrupt change can arrive without warning. For centuries, the world warmed after the last glacial maximum. Forests grew, animals prospered, and humans explored new ways of living. Then, almost instantly in geological terms, warmth vanished and cold returned. For over 1,000 years, that state held, until it ended just as abruptly. The people living through these swings had no way to foresee them or to understand their deeper causes. We, with our scientific knowledge, are in a different position. We can see early signs of change and model potential futures, but we still risk being caught off guard if we assume that climate will always shift slowly and predictably. And yet, the story of the Younger Dryas is not only a cautionary tale, it is also a story of renewal. Just as abruptly as the cold began, it ended. The earth warmed, forests came back, animals multiplied. Humans not only survived, but seized this new opportunity to construct more complex societies. Out of hardship emerged growth. Out of scarcity came invention. This does not mean that our own climate crisis will resolve itself in the same way. The Younger Dryas was driven by natural forces. Today's change is largely of our own making. That difference places more responsibility on us. We cannot control volcanic eruptions or cosmic impacts, but we can decide how much carbon we emit, how we use land, and how we prepare for known risks. The Younger Dryas shows us what kind of disruption is possible when major components of the climate system are disturbed. It is up to us to decide whether we will push our current system towards similar tipping points, or whether we will act to keep it within safer bounds. For those who lived through the Younger Dryas, the lessons were direct. Stay flexible, diversify foods, cooperate with neighbors, and pass down stories of past upheavals. For us, the lessons must be expanded. Respect the sensitivities of the climate system, recognize the unevenness of impacts, invest in both mitigation and adaptation, and remember that sudden change is always possible. The Younger Dryas is not just a chapter of distant prehistory. It is a message from an earlier time, etched into ice, soil, fossils, and the faint echoes of myth. It reminds us that the planet's rhythms do not always align with human expectations, that the world can change quickly, and that our survival depends on our ability to understand, anticipate, and adapt. As we look back at that long-ago winter, we see both the vulnerability and the strength of our species. Vulnerability, because we are deeply dependent on climate and ecosystems we cannot fully control. Strength, because even under extreme stress, humans found ways to endure and to build anew. That duality, frail and resilient at once, is part of our inheritance from the Younger Dryas. The Younger Dryas is a story of sharp disruption, persistent resilience, and deep transformation. But it is also part of a larger pattern, the ongoing rhythm of Earth's climate. Our planet has never been static. Its temperatures, sea levels, ice coverage, and ecosystems have always risen and fallen in complex cycles driven by orbital shifts, volcanic activity, solar changes, and interactions between oceans, ice, and atmosphere. Ice ages come and go. Warm intervals wax and wane. Continents move, mountains rise and erode, and life constantly adjusts. The Younger Dryas was one particularly dramatic beat in this long rhythm, a sudden jarring pause in a warming trend, followed by a quick jump into a new climatic state. It stands out in our records because it happened so quickly and affected human societies at a critical moment. Yet it also reminds us that change is the rule, not the exception, in Earth's history. Today, we are living in the Holocene, the relatively mild, stable epoch that began when the Younger Dryas ended. For about 11,700 years, this stability has allowed agriculture and civilization to flourish. But that does not mean the underlying rhythms have stopped. Orbital cycles continue to shift. Ice sheets respond, currents flow and meander. On top of these natural processes, humans have now added a powerful new force, the rapid emission of greenhouse gases and widespread alteration of landscapes. This combination, natural rhythms plus human influence, makes our future both fragile and uncertain. The Younger Dryas tells us that abrupt shifts are possible even without human involvement. Now, with our added impact, we are accelerating some of the very mechanisms that have driven past changes. We are warming the atmosphere and oceans, melting ice sheets, and freshening parts of the North Atlantic, all processes that echo the factors involved in the Younger Dryas. But fragility does not mean inevitability. The rhythms of the Earth are vast, operating on timescales far longer than a human life. Our task is not to stop those rhythms. That would be impossible. Rather, it is to understand them, to recognize how our actions interact with them, and to make choices that avoid the most dangerous outcomes. We cannot prevent the next ice age forever, or the eventual rise and fall of seas in the distant future. We can, however, decide how much we will amplify or dampen certain near-term changes, and how prepared we will be to face them. The Younger Dryas invites humility. It shows that entire regional climates can transform within a single human lifetime, and that ecosystems and cultures must scramble to keep up. It also invites perspective. Over tens of thousands of years, Earth has passed through many such transitions and will continue to do so long after our current societies are gone. In the face of that deep time, our infrastructures and institutions are delicate. They depend on a narrow range of conditions that we sometimes take for granted: steady sea levels, relatively predictable weather, fertile soils. At the same time, the Younger Dryas offers a kind of reassurance. It proves that humans are capable of surviving in the midst of abrupt change, that we have an impressive capacity for adaptation. The key difference now is that we have far more people, far more complex systems, and far greater power to alter the environment. That amplifies both our vulnerability and our responsibility. Our globalized civilization means that disruptions in one region can propagate quickly through economic and social networks. A drought in a major grain-producing area can influence food prices worldwide. A flood that damages a critical port can impair supply chains across oceans. In this way, our human systems now resemble the climate system itself, intricately connected, capable of rapid cascading effects when one part is stressed. Within this fragility, there is also continuity. The same ingenuity and cooperation that allowed people to survive the Younger Dryas still exist. Advances in science and technology give us tools to monitor and model climate in ways our ancestors could not have imagined. International agreements, while imperfect, reflect a growing recognition that climate is a shared concern. Local adaptation efforts from redesigned cities to restored wetlands show that creative responses are possible. The deeper challenge lies not in our lack of capacity, but in the mismatch between the speeds at which different systems operate. Physical climate processes can accelerate quickly once thresholds are crossed. Political and social systems often move more slowly, constrained by inertia, conflict, or short-term thinking. The history of the Younger Dryas suggests that waiting for clear, immediate signs of crisis before acting can be dangerous, because when change comes abruptly, preparation time is limited. Memory, once again, plays a crucial role. Ancient people encoded their experiences of dramatic change in myth and tradition. We encode ours in data and reports. Both are forms of narrative, and both risk being ignored if they are not woven into the decisions we make every day. If we treat scientific warnings as distant abstractions rather than as living memories of what the Earth is capable of, we may find ourselves repeating patterns of unpreparedness. Looking ahead, the rhythms of Earth will continue. Ice will grow and shrink. Oceans will warm and cool. Forests will advance and retreat. Over long timescales, new Younger Dryas-like episodes may come and go, regardless of whether humans are present to witness them. Our concern, however, is with the more immediate horizon, the coming decades and centuries in which our choices can still significantly influence outcomes. The story of the Younger Dryas thus serves both as a mirror and as a message. As a mirror, it reflects what abrupt climate change looks like, how it feels, how it ripples through plants, animals, and people. As a message, it urges us to take seriously the possibility of rapid shifts, to build systems that can absorb shocks, and to act in ways that reduce the likelihood of pushing our own climate system past similar thresholds. We cannot control the Earth's deep rhythms, but we can choose whether our societies are brittle or flexible, whether our infrastructures are rigid or adaptive, and whether our decisions are guided by short-term convenience or long-term foresight. In the end, the Younger Dryas reminds us that we live on a restless planet. The climate is not a fixed background. It is an active, changing presence. 12,000 years ago, people faced a world transformed almost overnight. They endured, and from their endurance, the foundations of civilization emerged. Today, as we face our own era of rapid change, this time driven largely by our own actions, we stand at another crossroads. Our task is to remember, to prepare, and to act wisely within the fragile balance we now inhabit. The Younger Dryas, etched into ice cores, sediments, and stories, tells us that change can be sudden and far-reaching. It also tells us that survival is possible, but not guaranteed. Our future will depend on how seriously we take those lessons, and on whether we can match the resilience of our ancestors with the added insight that science and history now afford us. As we think about the Younger Dryas, we are not just revisiting an ancient climate episode. We are being reminded that the Earth does not move on human schedules. Its systems respond to forces that can build slowly over thousands of years and then express themselves in sudden, dramatic shifts. The Younger Dryas was one such shift, a rapid descent into cold, a long season of testing, and a swift rise into warmth. It transformed landscapes, ecosystems, and human societies, and it did so with little warning. 12,000 years ago, people had no control over the forces that shaped their climate. They did not choose the meltwater pulses, the volcanic eruptions, or any possible cosmic encounters that might have nudged the planet into the Younger Dryas. They simply faced the consequences. Today, we are in a different position. We have become a major force in the climate system, altering the composition of the atmosphere, reshaping land surfaces, and influencing oceans and ice. That gives us a responsibility our ancestors did not bear. The Younger Dryas shows us the kind of world-altering change that can occur when large components of the climate system are disturbed. It also shows us how quickly change can unfold within the span of a single life. Our global civilization, with its dense cities, vast infrastructure, and interdependent economies, is more sensitive to such shifts than the small mobile bands of the late Pleistocene. A drought that once might have forced a few hundred people to move can now affect millions. A flood that once scoured a single valley can, when combined with modern settlements, cause damage on a global economic scale. And yet, our strengths have also grown. We can monitor the planet from space, measure gases in the atmosphere, track the flow of heat in the oceans, and model possible futures with unprecedented detail. We can share information instantly across continents, coordinate responses, and learn from one another's experiences. These abilities do not eliminate risk, but they widen the range of choices available to us. The kind of resilience cultivated during the Younger Dryas, flexibility, cooperation, the ability to diversify and innovate, remains as valuable as ever. In some ways, it is even more essential because the systems we now depend upon, electrical grids, global supply chains, large-scale agriculture, are both powerful and fragile. They provide great benefits but can also fail quickly if not designed with change in mind. The Younger Dryas asks us to think not only about how we reduce our impact on the climate, but also about how we prepare for the impacts that are already inevitable. It suggests that we should build redundancy into our food systems, protect and restore ecosystems that buffer floods and storms, and design cities and infrastructure that can withstand both gradual changes and sudden extremes. It encourages us to value local knowledge and community ties, just as ancient peoples did, because in times of disruption, neighbors and local networks are often the first and most reliable line of support. There's also an ethical dimension that the Younger Dryas helps to illuminate. Climate change does not affect all people equally. During the Younger Dryas, some regions became uninhabitable while others became more favorable. Some groups were forced to migrate and adapt under severe stress, while others found new lands to exploit. Today, as climate shifts again, the costs are likewise uneven. Those who have contributed least to greenhouse gas emissions are often among the most vulnerable to their consequences. Understanding this unevenness and acknowledging the patterns of justice and injustice that accompany climate change is part of what it means to learn from the past rather than simply observe it. In the grand sweep of Earth's history, the Younger Dryas was a brief pause, a 1,000-year shiver on the path out of the last ice age. But for humans, it was long enough to matter deeply. It reshaped our ancestors' lives, redirected cultural trajectories, and helped steer humanity toward agriculture and civilization. Standing where we are now, at another moment of profound climatic transition, we can see in the Younger Dryas a kind of distant cousin to our own crisis, different in cause and context, but similar in its power to reorder the world. What we do with that knowledge is up to us. The Younger Dryas offers no guarantees, only guidance. That climate can change abruptly, that resilience is possible but must be cultivated, that innovation often emerges from hardship, that memory, whether in myth or in data, is vital, and that humility in the face of Earth's rhythms is wiser than the illusion of complete control. As you let these thoughts settle, you might imagine the people who lived through that ancient cold. Picture a small camp beneath a broad, starry sky, the air crisp with winter that never seems quite to end. A fire burns at the center, its light flickering on faces turned inward to listen. An elder speaks of a time when the land was greener, when the rivers flowed longer, when the great animals roamed in greater numbers. The children, wrapped in furs, listen with wide eyes. For them, such a world is almost unimaginable. Yet one day, perhaps within their lives or their children's, the world will change again. We too are gathered in a way, around a fire of shared information and story. We have our own elders, scientists, historians, indigenous knowledge keepers who tell us of past climates, past upheavals, and of what those events meant for life. We can choose to listen, to learn, and to prepare, or we can turn away and pretend the fire's light is all that exists, ignoring the darkness beyond. The Younger Dryas reminds us that the darkness is not empty. It holds ice and flood, fire and dust, but also resilience, creativity, and the possibility of renewal. Our task is to face it with open eyes, to remember that we are part of a living, changing planet, and to carry forward the lessons of those who endured great change before us. And so, as this story comes to a close, the Earth's long rhythms continue. The slow drift of continents, the turning of the seasons, the pulse of ice and warmth across ages. The Younger Dryas is one chapter in that immense narrative, a time when the planet's balance tilted, paused, and then righted itself in a new configuration. It is a reminder that our world has changed before and will change again, and that in every such change, life must decide how to respond. We are the latest expression of that decision, inheritors of an adaptability forged in cold and scarcity, now facing a different kind of challenge in a warming world of our own making. Whether we respond with wisdom and foresight, or with denial and delay, will shape the stories told about us in the distant future, perhaps around other fires, under other skies. For now, we can sit quietly with the knowledge that 12,000 years ago, people much like us faced a world that seemed to transform overnight. They met that transformation not with certainty or control, but with courage, cooperation, and imagination. It was enough to carry them through. As we listen to the echoes of their forgotten Earth, we might find in them the resolve to face our own changing world with the same unassuming strength.